Hello there, and welcome to Physics with William, where curiosity slows down just enough for us to take a proper look at the world around us. Tonight, we're turning our attention to something that sounds almost alarming when you first hear it. The Earth, the solid ground beneath your feet, the floor under your chair, the bed you may be lying in right now, is spinning at roughly 1,000 miles per hour. That's about 1,670 kilometers per hour at the equator. Faster than a commercial jet, faster than most rifle bullets. Fast enough that, on paper, it sounds like you should at least need to hang on to something, and yet here you are, not sliding sideways, not clinging to the carpet, not being flung dramatically into the night sky like a misplaced astronaut. The room is still. The air is calm. Nothing feels like it's racing eastward at extraordinary speed. So, what's going on? Before we dig into the physics, let me ask you something simple. Where are you listening from right now? Are you near the equator, where the rotational speed is at its maximum? Or are you farther north or south, where that speed quietly tapers off? And at this moment, as you hear this, what time is it for you? Morning light creeping in? Late evening winding down? Somewhere in between? It's worth noticing that the very concept of time of day depends entirely on the fact that the Earth is rotating beneath the Sun. If you find this kind of exploration calming or thought-provoking, consider liking the video and subscribing. It helps this quiet corner of science reach others who might appreciate taking a steady look at the mechanics of the universe. Now, let's settle into the question itself, because once you really consider it, the situation is stranger than it first appears. The Earth completes one full rotation approximately every 24 hours. The circumference of the planet at the equator is about 24,901 miles. Divide that by 24 hours and you arrive at a number just over 1,000 miles per hour. That means if you're standing at the equator, you're tracing a circular path through space at that speed, simply by remaining still relative to the ground. But you don't feel like you're moving at 1,000 miles per hour. You feel stationary. That contrast between what is happening physically and what is experienced subjectively is the first clue. Motion, as it turns out, is not something we detect in absolute terms. We detect changes in motion, acceleration, shifts, jerks, vibrations. When you're in a car that suddenly speeds up, you feel pressed back into the seat. When it brakes sharply, your body lurches forward. It's not the speed itself that you feel, it's the change in speed. If a plane cruises smoothly at 500 miles per hour and you close the window shade, you can forget you're moving at all. The coffee sits calmly on the tray. The cabin feels steady. Only turbulence or acceleration remind you that you're racing through the sky. In steady motion, your body relaxes into the frame of reference it occupies. The Earth's rotation is remarkably steady. It doesn't start and stop. It doesn't jerk forward and hesitate. It spins at a nearly constant angular velocity. Because there is no sudden acceleration in your daily experience, your body has no reason to register the movement. There's another important detail. Everything around you is rotating at exactly the same rate. The ground, the buildings, the oceans, the air, even the atmosphere shares in this rotation. So relative to your immediate environment, nothing is moving. You, the chair, the walls, and the air molecules are all travelling together. To understand why that matters, imagine standing on a massive rotating platform. If you and everything around you are firmly attached to that platform and it spins smoothly at constant speed, you would not notice the rotation unless you looked outward at something not rotating with you. The key word here is relative. Motion only becomes meaningful when compared to something else. Right now you feel stationary because you are stationary relative to the surface of the Earth. The speed of 1,000 miles per hour only appears when we compare you to a non-rotating frame of reference, such as distant stars. There is also the matter of gravity. Even if we accept that motion is relative and that steady rotation doesn't automatically produce a noticeable sensation, there's still the intuitive concern. Shouldn't spinning that fast try to fling you outward? This is where we need to consider forces more carefully. When something moves in a circle, it experiences what is known as centripetal acceleration, directed toward the center of the circle. Without this inward pull, an object moving in a curved path would travel off in a straight line according to Newton's first law of motion. On Earth, gravity provides that inward pull. It keeps you anchored to the surface. The gravitational force between you and the Earth pulls you toward the planet's center. At the same time, the Earth's rotation does create a small outward effect often referred to as centrifugal force in the rotating frame of reference. But the key word here is small. Let's compare magnitudes. The acceleration due to gravity at Earth's surface is approximately 9.8 meters per second squared. The outward acceleration caused by Earth's rotation at the equator is about 0.034 meters per second squared. That means the outward effect is less than half of 1% of gravity's pull. Gravity wins easily. In fact, your weight at the equator is slightly less than it would be if the Earth did not rotate. The difference is small, but measurable. If the Earth spun faster, that outward effect would increase. If it spun slowly enough, it would be almost negligible. But at its current speed, the rotational effect is nowhere near strong enough to overcome gravity. It's also worth noting that the Earth is not a perfect sphere. Because of its rotation, it bulges slightly at the equator. The equatorial diameter is about 43 kilometers larger than the polar diameter. This bulging is a direct consequence of rotation. Over billions of years, the planet has settled into a shape that reflects the balance between gravity pulling inward and rotational effects pushing outward. Even so, the structure remains stable. The gravitational binding of the planet is immense. To fling something into space, you must reach escape velocity, which is about 25,000 miles per hour. That's vastly greater than the rotational speed of 1,000 miles per hour. Simply standing on the surface doesn't bring you anywhere close to escaping Earth's gravitational grip. There's another layer to this that often surprises people. The Earth isn't just spinning, it's also orbiting the Sun at roughly 67,000 miles per hour, and the entire solar system is orbiting the center of the Milky Way galaxy at around 490,000 miles per hour. Meanwhile, the galaxy itself moves relative to other galaxies. Add those numbers together and you're traveling through the universe at extraordinary speed. Yet again, you feel nothing unusual. The explanation remains consistent. These motions are steady. They are shared. There is no sudden acceleration disrupting your frame of reference. Your body and everything around you participate in the motion together. Without an external, unmoving reference point to create a sense of contrast, the movement goes unnoticed. Consider what would happen if the Earth suddenly stopped spinning. That's when things would become noticeable in a very dramatic way. The ground beneath you would halt, but your body would continue moving eastward at the previous rotational speed due to inertia. The atmosphere would continue moving as well. The result would be catastrophic winds, structural devastation, and massive redistribution of oceans. The reason we don't experience that chaos is precisely because the rotation is continuous and consistent. Inertia plays a central role here. Objects in motion remain in motion unless acted upon by an external force. You're already in motion, moving eastward along with the Earth. There is no force trying to change that motion dramatically under normal circumstances, so you continue moving along with the planet without noticing it. It's also helpful to reflect on how our senses evolved. Humans did not develop sensory organs to detect constant linear or rotational velocity relative to distant cosmic objects. We evolved to detect changes that matter for survival: acceleration, imbalance, impact. The inner ear contains structures that detect rotational acceleration, not constant rotation. Once rotation becomes steady, the fluid in the semicircular canal stabilizes and the sensation fades. That's why if you spin in a chair and then stop abruptly, you feel dizzy. Your inner ear registers the change in rotation. But if you were placed on a perfectly smooth rotating platform that gradually reached a constant speed, and then remained there, you might lose awareness of the rotation entirely. The Earth's rotation is the ultimate example of such smooth, long-term motion. It has been spinning for over 4 billion years. There was no moment in your personal experience when it started. There is no daily jolt reminding you of its presence. It simply continues. At this point, the situation begins to feel less mysterious. The combination of gravity's dominance, shared motion of everything around you, inertia, and the nature of human perception all contribute to the same outcome. The Earth can spin at 1,000 miles per hour without tossing you into space because you're not an object perched precariously on a rotating disk. You're part of a massive, gravitationally bound system, moving in coherent, stable motion. Still, questions naturally follow. If gravity is holding everything together, how strong would the rotation need to be to counteract it? What if Earth rotated twice as fast, or 10 times as fast? Would the equator become uninhabitable? And how does this rotation influence weather systems, ocean currents, and the very shape of the planet? Those are not hypothetical curiosities. They connect directly to how the world functions on a daily basis. The spinning of the Earth shapes the length of a day, the cycle of temperature, wind patterns, and even the path of storms. The rotation is not just a background detail, it is an active factor in the planet's behaviour. For now, though, it's enough to recognise that what feels like stillness is often motion viewed from within. The floor feels solid and unmoving, but it is carrying you through space at tremendous speed. You're not being thrown off because the forces involved are balanced in a stable way, and because your senses are tuned to detect change rather than constant motion. In a moment, we'll look more closely at what relative motion really means, and how it reframes our understanding of speed itself. Because once you start comparing different frames of reference, the idea of being at rest becomes more subtle than it first appears. When people first hear that the Earth spins at roughly 1,000 miles per hour, the immediate reaction is usually disbelief. It sounds exaggerated, almost like one of those statistics designed to grab attention rather than describe something real. 1,000 miles per hour is the cruising speed of a high-performance aircraft. It's the kind of number associated with supersonic travel, not with sitting quietly in a chair or walking across a room. And yet, at the equator, that figure is entirely accurate. The calculation itself is straightforward. The Earth completes one full rotation in about 24 hours. The circumference of the planet at the equator is approximately 24,901 miles. Divide that distance by the time it takes to complete a rotation, and you get just over 1,000 miles per hour. If you're standing at the equator, you're tracing a circular path through space at that speed, simply by remaining still relative to the ground. But this immediately raises a deeper question. When we say you are moving at 1,000 miles per hour, what exactly are we measuring? Moving relative to what? Speed, unlike distance, is not an absolute property. It only has meaning when compared to something else. If you're sitting in a parked car, your speed relative to the car is 0. Your speed relative to the Earth's surface is also 0. But your speed relative to the centre of the Earth is not 0, because you are participating in the planet's rotation. Your speed relative to the Sun is even larger, because the Earth orbits the Sun at about 67,000 miles per hour. And relative to the centre of the Milky Way galaxy, you are moving at roughly 490,000 miles per hour. So which one is your real speed? This is where the concept of a frame of reference becomes essential. A frame of reference is simply a perspective from which motion is measured. In physics, we often choose a convenient frame depending on the problem we are solving. If we're calculating how long it takes to drive from one city to another, we measure speed relative to the ground. If we're studying planetary motion, we might measure speed relative to the Sun. There is no universal privileged frame that defines motion once and for all. From your everyday perspective, you are at rest. The chair is not sliding beneath you. The walls are not racing past. The air is not streaming horizontally at hurricane speeds. Within the frame of reference of the Earth's surface, you are stationary. That statement is just as valid as saying you're moving at 1,000 miles per hour relative to distant stars. This might feel like a technical distinction, but it's fundamental. Motion is not something an object possesses by itself. It is always motion relative to something else. Without a comparison, the concept of speed has no meaning. To make this clearer, imagine you're on a train travelling at 100 miles per hour. You stand up and walk forward down the aisle at 3 miles per hour relative to the train. To someone sitting on the train, you're moving at 3 miles per hour. To someone standing on the ground watching the train pass, you're moving at 103 miles per hour. Both observers are correct within their own frames of reference. The same logic applies to the Earth's rotation. Within the rotating frame of the Earth, you're not sliding eastward at 1,000 miles per hour. You're at rest relative to the ground. The 1,000 mile per hour figure only emerges when you compare your motion to an external, non-rotating reference, such as distant stars. There's another important point here. The speed of 1,000 miles per hour only applies at the equator. If you're located farther north or south, your speed due to rotation is lower. This is because you are tracing a smaller circle each day. At the poles, the rotational speed is effectively zero. You still complete one rotation every 24 hours, but you're rotating in place rather than travelling along a wide circular path. This happens because the Earth is spherical. Points on the equator have the largest possible circumference to travel during each rotation. As you move toward the poles, the circumference of your daily path shrinks. The angular speed is the same everywhere, one full rotation per day, but the linear speed depends on the radius of the circle you're tracing. So if someone asks, "Are you really moving at 1,000 miles per hour?" the honest answer is, it depends on where you are and what you're measuring against. At the equator, relative to distant stars, yes. At higher latitudes, the speed is lower. Relative to the Earth's surface beneath your feet, you're not moving at all. This is often counterintuitive because we tend to think of speed as something intrinsic. A car has a speed. A plane has a speed. But even in those cases, the speed is always relative to something. When a speedometer reads 60 miles per hour, it means 60 miles per hour relative to the road. If the road itself were sliding sideways, that number would no longer tell the whole story. Now consider how your body detects motion. You do not have a built-in sensor for constant velocity. What you feel are changes in velocity, acceleration. When a car speeds up, you feel pressed into your seat. When it turns sharply, you feel pulled sideways. But if the car moves at a steady speed on a smooth highway, you can close your eyes and forget you're moving. The Earth's rotation is steady and consistent. There is no daily acceleration from 0 to 1,000 miles per hour. You were born into a system already rotating. Every second of your life has taken place within this rotating frame. Your body has no baseline experience of non-rotation against which to compare it. It's similar to being on a large, smoothly rotating platform in a completely enclosed room. If the rotation is constant and you have no view outside, you may not perceive it directly. Objects around you remain stationary relative to you. The air moves with you. There is no visual cue indicating motion. The only hint of rotation would come from subtle forces, like the slight outward effect due to circular motion. But as we've already established, the outward acceleration from Earth's rotation is tiny compared to gravity. It slightly reduces your weight at the equator, but not enough for you to notice without precision instruments. Let's examine that outward effect more closely, because it helps clarify whether 1,000 miles per hour is something to worry about. When an object moves in a circle, it requires an inward force to keep it from flying off in a straight line. On Earth, gravity provides that inward force. The outward tendency associated with circular motion is proportional to the square of the speed divided by the radius of the circle. Even though 1,000 miles per hour sounds large, the radius of the Earth is enormous, about 6,300 to 71 kilometers. Because the radius is so large, the curvature of your path is extremely gentle. You're not whipping around a tight circle like a stone on a string. You're following a vast arc with a huge radius, which means the required centripetal acceleration is relatively small. That's why the outward effect is only about 0.3% of gravity at the equator, Gravity pulls you inward with far greater strength than rotation pushes you outward. If the Earth spun much faster, the balance would shift. At a rotation period of about 84 minutes, roughly 17 times faster than today, the outward acceleration at the equator would equal gravity. At that point, objects at the equator would effectively become weightless. But we are nowhere near that scenario. The Earth's current rotation rate is well within the range that gravity easily dominates. It's also worth stepping back and noticing something broader. The number 1,000 miles per hour feels dramatic because of human-scale comparisons. We compare it to airplanes or bullets, because those are speeds we associate with danger or power. But in astronomical terms, 1,000 miles per hour is modest. Earth's orbital speed around the Sun is about 67,000 miles per hour. The Sun itself orbits the centre of the galaxy at roughly 490,000 miles per hour. Compared to those motions, Earth's rotation is relatively slow. The only reason 1,000 miles per hour sounds impressive is because we are used to living at ground level, where most of our movements happen at walking or driving speeds. From a cosmic perspective, you are always moving at extraordinary speeds. The idea of being still is a local illusion created by shared motion within a stable frame of reference. If we were to freeze the Earth's rotation but leave its orbit unchanged, you would still be travelling around the Sun at tens of thousands of miles per hour. If we froze the solar system's motion within the galaxy itself would continue moving relative to other galaxies. There is no universal point of rest in the universe. Everything is moving relative to something else. So are you really moving at 1,000 miles per hour? Yes, in one sense. No, in another. The statement is true when measured against a non-rotating external reference. It is false within the everyday frame in which you live and interact. The more useful question might be this: does that speed have any practical consequence for your daily life? The answer is largely no. The rotation of the Earth shapes the length of the day, influences weather systems through the Coriolis effect, and contributes to the planet's equatorial bulge. But it does not produce dramatic sensations because it is steady, shared, and balanced by gravity. Understanding this helps reframe what we mean by speed itself. Speed is not an absolute label attached to you. It is a description that depends entirely on perspective. And once we accept that, the 1,000 mile per hour figure becomes less alarming and more intriguing, because if motion is always relative, then the next logical step is to explore how that relativity shapes our entire understanding of physics, from trains and airplanes to planets and stars, and why the concept of being at rest is far more subtle than it first appears. If the Earth is rotating at such remarkable speed, the natural follow-up question is not just whether you're moving that fast, but why you don't experience it directly. 1,000 miles per hour sounds like it should come with a sensation. We associate high speed with force, pressure, vibration, noise, yet the ground feels steady. A glass of water sits calmly on the table. There is no constant rushing sound of air tearing past you. So what exactly prevents you from feeling the spin? The answer begins with how human beings detect motion in the first place. Your body does not measure speed directly. It measures changes in speed. In physics, that distinction is the difference between velocity and acceleration. Velocity is speed in a particular direction. Acceleration is a change in velocity, whether that change involves speeding up, slowing down, or changing direction. When a car accelerates from a stoplight, you feel pushed back into your seat. That sensation is your body resisting the change in velocity. When the car brakes suddenly, you feel thrown forward. Again, it is the change that your body detects. If the car cruises smoothly at a constant speed on a straight highway, the sensation fades. You can close your eyes and forget you're moving at all. The Earth's rotation is constant. It does not speed up every morning and slow down every night. It completes one full rotation in roughly 24 hours with remarkable regularity. Because the speed is steady, your body has no abrupt change to register. There is no daily jolt to remind you that the ground is moving. But the Earth's rotation is not linear motion, it is circular motion. Circular motion involves continuous change in direction, even if the speed remains constant. So technically, there is acceleration present. In circular motion, the acceleration is directed toward the center of the circle. On Earth, that center is the planet's core. This inward acceleration is known as centripetal acceleration. Without it, you would move off in a straight line rather than follow the curved surface of the Earth. The source of that centripetal force is gravity. Gravity pulls you toward the center of the Earth, continuously redirecting your motion so that you follow the planet's curvature. The key detail is that the required centripetal acceleration for Earth's rotation is very small compared to gravity itself. At the equator, the outward effect associated with rotation is only about 0.3% of the gravitational pull. Gravity is far stronger. The net force pressing you against the ground is almost entirely gravitational. The rotational effect merely reduces your effective weight slightly. Because that rotational acceleration is small and constant, your body does not interpret it as motion in the everyday sense. It simply becomes part of the stable balance of forces that define your normal experience. There is also the matter of shared motion. Everything around you is rotating at exactly the same rate as you are. The ground, buildings, oceans, atmosphere, and even the air molecules in your lungs are all participating in the same rotational motion. There is no wind caused by the Earth spinning beneath a stationary atmosphere. The atmosphere rotates with the planet because it is gravitationally bound to it. Imagine sitting inside a sealed train car moving at constant speed on perfectly smooth tracks. If you toss a ball straight up, it comes straight back down into your hand. It does not fly toward the back of the train. That is because you, the ball, and the air inside the train are all moving together at the same velocity. Within that enclosed system, everything appears stationary relative to everything else. The Earth functions in much the same way. We live inside a gravitationally bound, rotating system. Because we share that motion, there is no relative movement between us and our immediate surroundings to generate a sensation of speed. Your sensory systems reinforce this. The inner ear contains structures called semicircular canals that detect rotational acceleration. These canals are filled with fluid. When your head begins to rotate, the fluid lags slightly behind due to inertia, bending tiny hair cells that send signals to your brain. That is how you detect spinning. However, if the rotation becomes steady and continuous, the fluid eventually catches up. Once it moves at the same rate as the canal walls, the bending of the hair cells stops. The sensation of rotation fades. This is why, if you spin slowly in a chair and maintain that spin at a constant rate, the feeling of rotation diminishes. When you stop abruptly, the fluid continues moving briefly, creating the sensation that you are spinning in the opposite direction. The Earth's rotation is so smooth and gradual that your inner ear has never experienced a starting point. There was no moment in your life when the planet began spinning. You were born into a rotating system. From the perspective of your sensory organs, this is the baseline state. Visual cues also play a role in how we perceive motion. When you are in a car, you feel like you're moving because the scenery outside the window flows past you. If you are in a windowless cabin with no vibrations or acceleration, the sensation of motion largely disappears. On Earth, the landscape is not sliding beneath you, it rotates along with you. There is no visual evidence of eastward movement because everything in your field of view shares the same motion. If you look at distant stars, you do see apparent motion over the course of hours. The stars appear to rise and set. But because that motion is slow and predictable, it does not trigger a bodily sensation of spinning. Instead, we interpret it as the sky moving, even though the actual cause is Earth's rotation. There is another factor to consider: scale. The radius of the Earth is about 6,371 kilometers. When you move in a circle of that size once every 24 hours, the curvature of your path is extremely gentle. The change in direction from one moment to the next is almost imperceptible. You're not swinging around a tight loop, you're tracing an enormous arc. To feel strong rotational effects, the radius of rotation must be small or the speed must be much higher. If you spin on a playground merry-go-round, you feel the outward pull clearly because the radius is small and the angular speed is relatively high. The forces involved are large compared to your body weight. On Earth, the ratio is tiny. This is also why astronauts in orbit experience weightlessness, even though they are moving at about 17,500 miles per hour. They are in continuous free fall around the Earth. The speed is high, but the motion is smooth and unchanging. There is no surface pushing back against them. In our case, gravity pushes us toward the center of the Earth, while the ground provides an upward normal force that balances it. The rotational component slightly modifies that balance, but does not dominate it. It is also important to remember that you're not a loose object perched on top of a spinning disk. You're gravitationally bound to the planet. Gravity is not a weak glue barely holding you down. It is a powerful force resulting from the mass of the entire Earth acting on every kilogram of your body. To escape that force, you would need to reach escape velocity, about 25,000 miles per hour. The rotational speed of 1,000 miles per hour is nowhere near sufficient. Some people imagine that because the Earth spins, there should be a constant wind blowing from west to east at extreme speed. That would only happen if the atmosphere were not rotating with the planet. In reality, the atmosphere formed from the same material as the Earth and remains gravitationally attached to it. It shares in the planet's rotation. Weather patterns arise from temperature differences and pressure gradients, not from the planet spinning beneath a stationary layer of air. There are subtle effects of rotation that we can measure. The Coriolis effect, for example, influences the direction of large-scale weather systems. Storms rotate differently in the northern and southern hemispheres because of the Earth's rotation. Long-range projectiles deviate slightly from straight-line paths due to rotational effects. Foucault pendulums demonstrate the rotation of the Earth by gradually changing their plane of swing relative to the ground. But none of these effects translate into a bodily sensation of spinning. They are observable with instruments or careful measurement, not with your balance system. There is also a psychological component. Human perception is tuned to detect changes that are relevant to survival. Sudden acceleration might signal danger. A shift in balance might indicate a fall. Constant, predictable motion that has never varied within your experience does not demand attention from the brain. Your brain builds a model of the world based on consistent input. In that model, the ground is stable, the sky moves overhead, the sun rises and sets. From a scientific perspective, we know that interpretation is inverted. The Earth rotates while the sun appears to move, but your sensory system does not need to resolve that distinction for you to function effectively. When you combine all these factors, constant velocity, shared motion of everything around you, gravity's dominance over rotational effects, the enormous radius of the Earth, and the design of your sensory systems, the mystery largely dissolves. There is no contradiction between spinning at 1,000 miles per hour and feeling completely still. The number only seems dramatic because we are comparing it to everyday speeds without considering the frame of reference. Understanding why you do not feel the Earth spin opens the door to a broader realization. Much of what we call stillness is simply motion viewed from within a moving system. Once you begin thinking in terms of frames of reference and shared motion, the concept of standing still becomes more nuanced, and that perspective becomes even more important when we look beyond Earth itself to the larger motion shaping our place in space. If you say that you're moving at 1,000 miles per hour because the Earth is rotating, the next logical question is simple and unavoidable. Moving compared to what? That small addition, compared to what, changes everything. It forces us to confront a fundamental principle in physics that is easy to state but surprisingly deep in its consequences. Motion is relative. There is no built-in cosmic speedometer assigning absolute velocities to objects in the universe. every statement about motion requires a reference point. In everyday life, we rarely notice this because our reference frame is assumed. When someone says a car is travelling at 60 miles per hour, they mean 60 miles per hour relative to the road. If the road itself was sliding beneath the car on a giant conveyor belt, that number would need clarification. The speed would depend on whether you measured it relative to the belt, the ground beneath the belt, or something else entirely. This may sound abstract, but it is the key to understanding why the Earth's rotation does not create chaos. When we say the Earth spins at roughly 1,000 miles per hour at the equator, we are measuring that motion relative to distant stars, or more precisely, relative to a non-rotating frame aligned with distant astronomical objects. From that perspective, a point on the equator traces a full circle every 24 hours, covering nearly 25,000 miles. That produces the familiar 1,000 mile per hour figure. But if you shift your reference frame to the surface of the Earth itself, your speed becomes zero. You're not sliding across the ground. The ground and you share the same motion. In this Earth-fixed frame, you are at rest. Neither description is more true than the other. They are both valid within their chosen frames. The apparent contradiction only arises if we assume there must be one absolute correct speed that applies in all contexts. To see why that assumption fails, consider a simple scenario. You're sitting on a train moving at a constant 100 miles per hour relative to the tracks. Inside the train, you toss a coin straight up. To you, the coin rises and falls vertically, landing back in your hand. To an observer standing on the platform outside, the coin follows a curved path through the air, moving forward along with the train while also rising and falling. Both descriptions are accurate within their respective frames of reference. The laws of physics work consistently in both frames. Inside the train, you do not need to account for the train's forward motion when predicting where the coin will land. The forward velocity is shared by you, the coin, and the air inside the train. From your perspective, everything behaves as though the train were stationary. The Earth functions in much the same way. We live inside a rotating system. The atmosphere, oceans, buildings, and people all share that rotation. Within this rotating frame, the physics of everyday life proceeds normally. A ball thrown straight up comes straight back down. A glass of water does not drift sideways. We do not need to constantly correct for eastward motion, because we and everything around us already possess that motion. This principle has a long history in physics. Galileo Galilei was among the first to articulate it clearly in the 17th century. He argued that if you were below deck on a smoothly sailing ship, you would not be able to determine whether the ship was at rest or moving at constant velocity simply by observing the behaviour of objects around you. Water dripping into a bowl, fish swimming in a tank, or a ball tossed from one person to another would behave the same way whether the ship was stationary or moving steadily forward. Galileo's insight was that the laws of mechanics are the same in all inertial frames moving at constant velocity relative to one another. There is no experiment you can perform inside such a frame to detect uniform motion without looking outside. This idea later became central to Isaac Newton's formulation of classical mechanics. Newton introduced the concept of absolute space and absolute time, but even within his framework, uniform motion could only be described relative to something else. A body in motion remains in motion unless acted upon by a force, but motion itself still requires a reference. Centuries later, Albert Einstein pushed this idea further with his theory of special relativity. He proposed that not only are the laws of mechanics the same in all inertial frames, but so are the laws of electromagnetism, including the speed of light. This led to the conclusion that measurements of space and time themselves depend on the observer's motion. Two observers moving relative to one another can disagree about distances and time intervals, yet both be correct within their own frames. What remains consistent is not absolute motion, but the structure of the laws governing motion. Bringing this back to the Earth's rotation, the important distinction is between inertial and non-inertial frames. An inertial frame is one moving at constant velocity in a straight line. A rotating frame, like the Earth's surface, is technically non-inertial, because it involves continuous change in direction. This means that certain additional effects appear in such frames, such as the Coriolis force and centrifugal effects. However, for everyday human experience, the rotation is slow and the acceleration small enough that the Earth's surface behaves almost like an inertial frame for most practical purposes. We can treat it as at rest for daily activities without introducing significant error. If you step outside at night and look at the stars, you see them slowly arc across the sky. In the Earth-fixed frame, it appears that the heavens are rotating around us. From the perspective of someone far away in space, it is the Earth that is turning. Both descriptions account for the observed motion. The difference lies in which frame we choose to regard as stationary. The deeper point is that the universe does not provide a preferred backdrop labelled truly at rest. Even the cosmic microwave background radiation, which offers a useful large-scale reference frame, does not create an absolute rest state in the Newtonian sense. It simply gives us a convenient standard for measuring motion on cosmological scales. So when someone asks whether you are really moving at 1,000 miles per hour, the only meaningful reply is to specify the comparison. Relative to distant stars, yes. Relative to the Earth beneath you, no. Relative to the Sun, your speed is closer to 67,000 miles per hour. Relative to the centre of the Milky Way, it approaches 500,000 miles per hour. None of these speeds cancel the others. They coexist because they are measured relative to different frames. This can feel unsettling because it challenges the intuition that there must be a single, correct description of motion. We tend to think of stillness as a concrete state. But in physics, stillness is always local. You're at rest relative to your chair. Your chair is at rest relative to the floor. The floor is at rest relative to the Earth's surface. The Earth's surface is rotating relative to distant stars. Each statement is precise within its chosen context. If we imagine removing all reference points, no stars, no galaxies, no external markers, the concept of motion itself becomes meaningless. Without something to compare against, speed cannot be defined. This is why physicists focus on relative motion and observable effects rather than searching for absolute velocity. Understanding this helps dissolve the apparent contradiction in the Earth's rotation. The 1,000 mile per hour figure is not a hidden danger you're somehow ignoring. It is a measurement tied to a particular frame of reference. Within the frame you inhabit daily, the ground is stable and you are at rest. The broader implication is that motion in the universe is layered. At one scale, you're stationary in a room. At another, you're circling the Earth's axis. At another, you're orbiting the Sun. At another still, you're travelling around the centre of the galaxy. These motions do not conflict. They stack upon one another, and because the laws of physics operate consistently within each frame, your coffee remains in its cup, your feet remain on the ground, and your sense of balance remains undisturbed. Once you internalise that motion is always relative, the focus naturally shifts. If speed itself is not absolute, then the question becomes less about how fast you're moving, and more about how forces and accelerations shape what you actually feel. That leads directly to the next layer of the puzzle, the role of gravity, inertia, and the forces that keep you firmly grounded on a spinning world. If motion is relative and constant rotation does not by itself create a noticeable sensation, there is still a more fundamental question that needs a clear answer. Even if you don't feel the Earth spinning, what actually keeps you from being flung outward? What prevents the 1,000 mile per hour motion from overcoming your connection to the ground? The answer is gravity. Not as a vague idea, but as a measurable, persistent force generated by mass. Gravity is the reason your feet remain in contact with the surface of the Earth. It is the reason the oceans do not drift off into space. It is the reason the atmosphere stays wrapped around the planet instead of trailing behind it. At its simplest, gravity is an attractive force between masses. Every object with mass attracts every other object with mass. The strength of that attraction depends on two things: how massive the objects are and how far apart they are. The more massive the objects, the stronger the force. The greater the distance between them, the weaker the force. The Earth is enormous. Its mass is approximately 5.97 times 10 to the power of 24 kilograms. That is a number so large it is difficult to visualize in practical terms. What matters is that this immense mass generates a gravitational pull strong enough to accelerate objects toward its center at about 9.8 meters per second squared near the surface. That acceleration is what we commonly refer to as 1g. When you stand on the ground, gravity pulls you toward the center of the Earth. The ground pushes back upward with an equal force. That upward push is what you perceive as weight. If gravity was suddenly removed, there would be no force pressing you against the ground. You would float freely, just as astronauts do in orbit. Now compare this gravitational acceleration to the outward acceleration caused by the Earth's rotation. At the equator, the outward acceleration due to rotation is about 0.034 meters per second squared. That is tiny compared to 9.8 meters per second squared. In percentage terms, it is roughly 0.3 of 1% of gravity. In practical terms, gravity is more than 30 times stronger than the rotational effect trying to pull you outward. That imbalance is decisive. The outward tendency associated with circular motion simply does not come close to overcoming gravity's inward pull. It is important to clarify what we mean by outward tendency. When an object moves in a circle, it requires a centripetal force, a force directed toward the center of the circle, to maintain that curved path. Without such a force, the object would travel in a straight line, according to Newton's first law of motion. On Earth, gravity provides the centripetal force necessary to keep you moving in a circular path as the planet rotates. From the perspective of someone on the surface, it can feel as though there is a small outward force, often described as centrifugal force, but this is best understood as a consequence of being in a rotating frame of reference. In reality, what is happening is straightforward. Your body has inertia. Inertia is the tendency of an object to continue moving in a straight line, at constant speed, unless acted upon by a force. Because the Earth rotates, you are continuously being redirected toward the center of the planet by gravity. That inward pull prevents your inertia from carrying you off in a straight line tangent to the Earth's surface. If gravity were weaker, the story would change. If the Earth spun significantly faster, the outward acceleration would increase. There is a precise point at which the outward acceleration at the equator would equal gravity. At that rotation rate, objects at the equator would effectively experience weightlessness. The surface would no longer press upward strongly enough to counteract the outward tendency. For the Earth to reach that condition, its rotation period would need to shrink dramatically. Instead of taking 24 hours to complete one rotation, it would need to spin once roughly every 84 minutes. That is far faster than its current rate. At that speed, the equator would become unstable. Loose objects could drift away. The oceans would redistribute dramatically. The planet itself might begin to deform further, but the Earth's actual rotation rate is nowhere near that threshold. Its speed is well within the range that gravity easily dominates. There is also another factor that reinforces gravity's control. The Earth's mass is not concentrated at the surface. It extends deep beneath your feet. When gravity pulls you downward, it is not just the crust exerting force. It is the entire mass of the planet acting on you. That collective pull is enormous. This is also why the atmosphere remains bound to the Earth. Gas molecules move rapidly, some at speeds of over 1,000 miles per hour depending on temperature. Yet most of them do not escape into space because gravity holds them in. Only the fastest moving particles at the very upper edge of the atmosphere occasionally reach speeds high enough to overcome Earth's gravitational pull. The same principle applies to you. Your horizontal motion due to Earth's rotation is only 1,000 miles per hour at the equator. But to escape Earth's gravity entirely, you would need to reach escape velocity, about 25,000 miles per hour. That is the speed required to overcome gravitational attraction without further propulsion. That number puts the Earth's rotational speed in perspective. 1,000 miles per hour is not even close to the velocity required to break free of the planet's gravitational grip. There is another subtle effect of gravity interacting with rotation. The Earth is not a perfect sphere. Because of its rotation, the planet bulges slightly at the equator. The equatorial radius is about 21 kilometers greater than the polar radius. This bulging is the result of the balance between gravity pulling inward and rotational effects pushing outward. Even so, gravity remains the dominant force shaping the planet. The bulge is modest compared to the Earth's overall size. The planet has reached a stable equilibrium where gravitational attraction and rotational forces coexist without tearing the world apart. It is also worth remembering that gravity does not switch off when you jump. When you leap into the air, you carry your horizontal rotational motion with you. You do not land in a different spot because the Earth has moved beneath you. That would only happen if gravity stopped acting during your jump. Instead, gravity continuously pulls you toward the center of the Earth, keeping your motion aligned with the planet's surface. From a physics standpoint, you're in constant freefall toward the center of the Earth, just like the Moon is in constant freefall toward Earth. The difference is that the ground prevents you from falling any farther. The Moon, by contrast, is far enough away and moving sideways fast enough that it continuously falls around the Earth rather than into it. Gravity, then, is not merely a background force. It is the central factor that stabilizes the entire system. It binds the atmosphere, shapes the oceans, maintains your weight, and provides the inward acceleration required for rotational motion. Without gravity, the Earth's rotation would indeed cause chaos. The slightest outward motion would carry objects off into space. The atmosphere would disperse, the oceans would drift away, the planet itself would likely fragment. But gravity is not a fragile tether. It is a robust, planet-wide force generated by an immense mass. The rotational effects we've been discussing are small perturbations layered on top of that dominant pull. Understanding this shifts the focus. The question is no longer why you're not thrown into space despite the Earth spinning. The better question is how rotation and gravity interact to produce the stable, habitable environment we experience every day. Because the balance between inward gravitational pull and outward rotational tendency does more than keep you grounded. It shapes the planet's structure, influences sea level distribution, and contributes to subtle variations in weight depending on latitude. And once we look closely at those variations, we begin to see that the Earth's rotation is not just a background statistic. It leaves measurable fingerprints on the planet itself. When people imagine the Earth spinning at 1,000 miles per hour, the mental picture often resembles a carnival ride. A circular platform rotating so fast that anything not bolted down is thrown outward. In that scenario, the outward force is obvious and dramatic. You grip the rail, your body leans away from the center, loose objects slide toward the edge. So if the Earth is spinning, why does the same thing not happen at the equator? Why are people in Ecuador or Kenya not clinging to the ground while feeling a strong outward pull? Why do oceans not spill off into space? To answer that properly, we need to examine what is commonly called centrifugal force and how it actually operates in the context of a rotating planet. In circular motion, an object moving in a curved path requires a force directed toward the center of that circle. That inward directed force is known as the centripetal force. Without it, inertia would carry the object off in a straight line tangent to the circle. From an outside, non-rotating frame of reference, the physics is straightforward. The Earth rotates. A person standing at the equator moves in a circle once every 24 hours. Gravity provides the inward force required to keep that person following the curved surface, rather than flying off into space. However, from the perspective of someone standing on the rotating Earth, it can feel as though there is an outward force trying to pull objects away from the axis of rotation. This apparent outward force is what we call centrifugal force. It is not a separate physical interaction like gravity or electromagnetism. Instead, it arises when we analyze motion from within a rotating frame of reference. To understand the distinction, imagine standing on a spinning playground merry-go-round. If you hold onto a pole near the centre, you feel a pull outward. If you let go, you slide toward the edge. From your perspective on the platform, it feels as though something is pushing you away from the centre. But if an observer watches from outside standing on the ground, they describe the situation differently. They see your body trying to continue in a straight line due to inertia. The platform beneath you is rotating, and unless a force acts to redirect you inward, you will not follow that circular path. The inward force is provided by friction between your shoes and the platform, or by your grip on the pole. On Earth, gravity plays the role of that inward force. At the equator, you are moving in a circle with a radius roughly equal to the Earth's radius, about 6,371 kilometers. Because the radius is so large, the required inward acceleration is relatively small, even though the linear speed sounds large. We can quantify this. The outward acceleration associated with Earth's rotation at the equator is approximately 0.034 meters per second squared. Compare that with gravitational acceleration, which is about 9.8 meters per second squared. The outward acceleration is roughly 1/300th of gravity. This means gravity is overwhelmingly dominant. The net effect of rotation is to reduce your effective weight by about 0.3% at the equator. That is measurable with sensitive instruments, but it is not something you can feel directly. If you weigh 70 kilograms at the poles, you would weigh slightly less at the equator. Not because gravity disappears, but because part of gravity's inward pull is being used to provide the centripetal acceleration required for rotation. The surface does not need to push up quite as strongly to support you. This small difference is one reason the Earth is slightly flattened at the poles and bulged at the equator. Over billions of years, the outward effect of rotation has redistributed mass slightly, creating an equatorial bulge about 21 kilometers larger in radius than the polar radius. However, that bulge represents a stable equilibrium, not an ongoing process of material being flung outward. The planet has already adjusted to the balance between gravitational pull and rotational effects. The key point is that centrifugal effects increase with the square of speed. If the Earth rotated twice as fast, the outward acceleration would increase by a factor of 4. If it rotated 10 times as fast, the outward acceleration would increase by a factor of 100. At some critical rotation rate, the outward acceleration at the equator would equal gravitational acceleration. At that point, objects at the equator would effectively experience zero net force toward the center. They would become weightless relative to the surface. That rotation period would be about 84 minutes per full spin, far faster than the current 24-hour period. At such a rate, the Earth's structure would likely be severely altered. Oceans would migrate dramatically toward the equator. The equatorial bulge would become extreme. Structural stresses within the planet's crust would increase. But at the present rotation rate, we are nowhere near that threshold. The outward effect is simply too small. Another factor that prevents dramatic outward motion is that the atmosphere rotates along with the Earth. The air at the equator is also moving at approximately 1,000 miles per hour relative to distant stars. Because the air shares the planet's rotational motion, there is no continuous eastward wind generated solely by rotation. Weather systems are influenced by rotation, particularly through the Coriolis effect, but that influence manifests in the deflection of moving air masses rather than in a constant outward or sideways blast. It is also worth clarifying that centrifugal force is strongest at the equator and zero at the poles. At the poles, you are rotating in place. Your radius of rotation is effectively zero, therefore the outward acceleration is zero. That means your effective weight at the poles is slightly greater than at the equator, both because there is no outward reduction and because you are closer to the Earth's centre due to the equatorial bulge. The difference in weight between equator and poles is small but measurable. It is a direct consequence of rotation combined with the Earth's shape. If you jump straight up at the equator, you do not land west of your starting point because you carry your rotational velocity with you. The outward and sideways components of motion are already part of your state. gravity continues to pull you toward the center of the Earth during the jump, ensuring that you land close to where you started. The only time centrifugal effects become strongly noticeable is when rotation rates are high and radii are small. In laboratory centrifuges, for example, samples can experience accelerations many times greater than gravity because the rotation speed is high and the radius is modest. In such cases, materials are indeed forced outward dramatically. On Earth, the radius is vast and the rotation rate moderate. The resulting outward acceleration is minor. There is also an important conceptual shift here. The question is not why you are not flung off the equator. The more precise question is whether the outward acceleration from rotation is strong enough to overcome gravity. The answer, by a large margin, is no. Gravity binds you to the planet. The centrifugal effect slightly modifies the net force you experience, but it does not dominate it. Understanding this removes the sense of hidden danger associated with the 1,000-mile-per-hour figure. The number sounds large in isolation, but when placed in the context of planetary scale and gravitational strength, it becomes clear that the Earth's rotation is well within stable limits. This balance between inward gravitational force and outward rotational tendency is not accidental. It is part of the long-term evolution of the planet. Over billions of years, the Earth has settled into a rotation rate and shape that remains stable under the combined influence of gravity and angular momentum. And once you see how these forces interact at the equator, it becomes natural to ask how the planet's rotation affects its overall shape and structure. Because the Earth, as it turns out, is not quite the perfect sphere we often imagine. When we picture the Earth, the image that usually comes to mind is a perfect sphere. Globes in classrooms, digital renderings from space agencies, even simple icons on weather apps, all reinforce the idea of a smooth, symmetrical ball. For most purposes, that approximation works, but in strict physical terms, the Earth is not a perfect sphere. Its shape carries the imprint of its rotation. The proper term for the Earth's overall shape is an oblate spheroid. Oblate means slightly flattened at the poles and bulging at the equator. The difference is not dramatic when viewed on a small scale, but it is measurable and significant in planetary terms. The Earth's equatorial radius is about 6,378 kilometers. Its polar radius is about 6,357 kilometers. That means the equator is roughly 21 kilometers farther from the planet's center than the poles. In other words, if you were to travel from the center of the Earth outward, you would reach the surface sooner at the poles than at the equator. That difference exists because of rotation. As the Earth spins, every point on its surface traces a circular path around the axis of rotation. At the equator, that circular path has the largest possible radius. At higher latitudes, the radius of that daily circle shrinks. At the poles, the radius is effectively zero. You rotate in place rather than travelling along a large circle. Rotation introduces an outward effect, often described in the rotating frame as centrifugal force. As discussed earlier, this outward acceleration is small compared to gravity, but over geological time, even small persistent forces can reshape matter. The Earth formed about 4.5 billion years ago from a rotating cloud of gas and dust. As material accreted under gravity, it also conserved angular momentum, meaning the young planet spun. During its early history, much of the Earth was molten or semi-molten. In that fluid state, material could redistribute more easily in response to forces. Gravity pulled mass inward toward the center, tending to form a sphere because a sphere is the shape that minimizes gravitational potential energy for a given mass. But rotation pushed material slightly outward at the equator. The result was a compromise between these influences, a sphere slightly flattened at the poles and slightly bulged at the equator. That equilibrium shape reflects a balance between gravitational attraction and rotational effects. The faster a planet spins, the more pronounced the equatorial bulge. If Earth rotated significantly faster, the bulge would be larger. If it rotated more slowly, the shape would be closer to a perfect sphere. This phenomenon is not unique to Earth. Many planets in our solar system exhibit similar flattening. Jupiter and Saturn, which rotate much faster than Earth and are composed largely of fluid material, show dramatic equatorial bulges. Saturn in particular is noticeably flattened because it completes one rotation in about 10.7 hours. The Earth's 24-hour rotation period produces only a modest flattening. The 21-kilometre difference between equatorial and polar radii is small relative to the planet's overall size, but it is large enough to influence measurements of gravity, satellite orbits, and sea level. Gravity itself varies slightly across the surface of the Earth because of this shape. At the poles, you are closer to the Earth's centre, and there is no outward rotational effect reducing your effective weight. As a result, gravitational acceleration at the poles is slightly stronger than at the equator. At the equator, you are farther from the centre and also experience the maximum outward acceleration due to rotation. These two factors combine to make your effective weight slightly less at the equator than at the poles. The difference is small, roughly 0.5%, but it is measurable. Sensitive instruments can detect variations in gravitational acceleration depending on latitude. Surveying, satellite navigation, and geophysics all take these variations into account. The Earth's shape also affects the distribution of ocean water. Water responds to the combined effects of gravity and rotation. The oceans naturally settle into a shape that reflects the Earth's gravitational potential, which is slightly higher at the equator because of the bulge. As a result, mean sea level is not equidistant from the Earth's centre everywhere. At the equator, sea level is slightly farther from the centre than at the poles. This does not mean the oceans are deeper at the equator in a simple sense, because ocean depth depends on local topography and tectonic structure. But in terms of distance from the Earth's centre, the equatorial surface lies farther out. The term geoid is used to describe the shape of the Earth's mean sea level extended under the continents. The geoid is not a perfect spheroid either. It includes small variations due to uneven mass distribution within the Earth, such as mountain ranges, ocean trenches, and variations in crust density. These irregularities create subtle gravitational differences that satellites can measure. Modern measurements using satellites like GRACE and GOSI have mapped these variations in exquisite detail. They show that the Earth's surface is not a mathematically perfect ellipsoid, but a complex shape shaped by both rotation and internal structure. Despite these complexities, the oblate spheroid remains a useful approximation. The flattening of the Earth can be quantified by a parameter known as the flattening factor, defined as the difference between equatorial and polar radii divided by the equatorial radius. For Earth, this value is about 1 over 298. In other words, the Earth is very close to spherical but not exactly. The flattening has practical consequences beyond gravitational variation. Satellite orbits must account for the Earth's equatorial bulge. The bulge causes slight perturbations in orbital paths, leading to phenomena such as orbital precession. Engineers designing navigation systems, communication satellites, and Earth-observing spacecraft incorporate these effects into their calculations. Even long-distance artillery trajectories and ballistic missile paths are influenced by Earth's rotation and shape. The Coriolis effect and the oblate shape both contribute to subtle deviations from straight-line motion over large distances. It is also important to understand that the Earth's shape is not static over geological time. Tidal interactions with the Moon are gradually slowing the Earth's rotation. Billions of years ago, a day on Earth was significantly shorter. Fossil evidence from coral growth patterns suggests that hundreds of millions of years ago, there were more days in a year because each day was shorter. As the rotation rate decreases, the equatorial bulge slowly adjusts. The planet's shape evolves along with its angular momentum. These changes are extremely gradual, occurring over millions of years, but they reflect the ongoing interplay between gravity and rotation. The fact that the Earth is not a perfect sphere is direct evidence of its rotational motion. The bulge is a visible imprint of the forces that shape the planet. If the Earth did not rotate, it would settle into a shape much closer to a true sphere, Understanding the Earth's shape helps clarify why the 1,000-mile-per-hour rotation does not threaten stability. The planet has already adapted to that rotation. Its mass distribution reflects the balance between inward gravitational pull and outward rotational influence. Instead of imagining yourself perched on the edge of a spinning disk, it is more accurate to picture yourself on the surface of a gravitationally bound, slightly flattened spheroid that has been rotating smoothly for billions of years. The forces involved are stable and well within the limits that the planet's structure can accommodate, and once we recognize that the Earth's current rotation rate produces only a modest bulge, it becomes natural to ask what would happen if that rate changed significantly. If the planet spun faster, the bulge would grow. If it slowed down dramatically, the shape would adjust again. That leads directly to the next question. How sensitive is this balance? How much faster would the Earth need to spin before the outward effects began to seriously compete with gravity? The Earth's current rotation rate feels stable because it is stable. One rotation every 24 hours has defined the rhythm of life for as long as complex organisms have existed. But that number is not fixed by any universal law. It is simply the present state of a planet that formed with a certain amount of angular momentum and has been gradually slowing over billions of years due to tidal interactions with the Moon. So it is reasonable to ask what would happen if that rotation rate were different. What if the Earth spun faster? Not slightly faster by a fraction of a second per day, but noticeably faster. What if a full rotation took 12 hours instead of 24? Or 6 hours? Or 1 hour? The first thing to understand is that increasing the rotation rate would increase the outward acceleration associated with circular motion. That outward acceleration is proportional to the square of angular velocity. In simple terms, if the Earth rotated twice as fast, the outward acceleration would not merely double, it would increase by a factor of 4. At present, the outward acceleration at the equator is about 0.034 meters per second squared. Gravity pulls downward at roughly 9.8 meters per second squared. That means the outward effect is small, about 0.3% of gravity. If the Earth rotated twice as fast, completing one rotation in 12 hours, the outward acceleration at the equator would be about 4 times greater than it is now. That would still be small compared to gravity, but the difference would become more noticeable. Your effective weight at the equator would decrease further. The equatorial bulge would increase. The shape of the planet would respond over time. Because the Earth's interior is not perfectly rigid, material would redistribute. The equator would bulge more prominently as the outward force pushed mass away from the axis of rotation. The poles would flatten further. Ocean water would respond more quickly than solid rock. Water flows in response to changes in gravitational potential. A faster rotation would cause a greater redistribution of ocean mass toward the equator. Sea levels near the equator would rise relative to the poles. Now consider a more dramatic scenario. Suppose the Earth rotated once every 6 hours instead of 24. That is 4 times the current angular velocity. Because centrifugal acceleration depends on the square of angular velocity, the outward acceleration would be 16 times greater than it is now. 16 times 0.034 meters per second squared is about 0.54 meters per second squared. That is still less than gravity, but no longer negligible. Effective weight at the equator would decrease by more than 5%. People and objects near the equator would feel noticeably lighter. The equatorial bulge would grow significantly over geological time. Tectonic stresses would increase as the planet adjusted to the new balance between gravitational pull and rotational effects. Sea levels at the equator would rise further, potentially flooding equatorial regions while exposing more land near the poles. Weather patterns would also change dramatically. The Coriolis effect, which arises from Earth's rotation, would become much stronger. The Coriolis effect causes moving air masses to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection plays a central role in shaping large-scale atmospheric circulation. A faster rotation would intensify these deflections. Wind systems would organize differently. Storm tracks would shift. The structure of global circulation cells, such as the Hadley, Ferrel, and polar cells, would be altered. Tropical regions might become narrower. Mid-latitude weather systems could become more complex. The length of day would also shrink accordingly. A 6-hour day would mean 4 complete day-night cycles within what is currently a 24-hour period. Biological rhythms, including circadian cycles in humans and other organisms, would face enormous pressure to adapt. Life on Earth is deeply synchronized with the 24-hour cycle. Many biological processes depend on light and darkness, intervals of roughly that length. A much shorter day would require evolutionary adjustments across ecosystems. Now consider pushing the rotation further. If the Earth rotated once every 3 hours, the outward acceleration at the equator would be 64 times greater than it is now. That would produce an outward acceleration of about 2.2 meters per second squared. Gravity would still dominate, but effective weight at the equator would decrease by more than 20%. At this point, the structural integrity of the planet would come under serious stress. The equatorial bulge would become extreme. Ocean water would surge toward the equator, forming a pronounced equatorial band of deep water. Polar regions might become comparatively dry. Atmospheric dynamics would be radically different. The stronger Coriolis effect would likely fragment weather systems into narrower, faster-moving bands. Wind speeds could increase significantly. The difference in temperature distribution between equator and poles might shift in unpredictable ways. Finally, consider the theoretical threshold at which outward acceleration equals gravity at the equator. That occurs when the centripetal acceleration required for rotation matches gravitational acceleration, about 9.8 meters per second squared. For Earth's size, this would require a rotation period of roughly 84 minutes. That is about 17 times faster than the current rotation rate. At that speed, the outward acceleration at the equator would equal gravity. Effective weight at the equator would drop to 0. Objects at the equator would become weightless relative to the surface. A slight disturbance could allow material to drift away. The oceans would not simply rise. They would struggle to remain attached to the planet at the equator. The planet's structure would likely fail before reaching this exact point. Rock is strong, but it has limits. The stresses generated by such rapid rotation could fracture the crust. The Earth might deform into a much more extreme oblate shape, potentially becoming unstable. In extreme cases, if a rotating body spins fast enough, it can shed mass from its equator. Some rapidly rotating stars exhibit this behavior, ejecting material into space. For Earth, reaching such a condition would require energy input far beyond any natural process currently at work. It is important to note that the Earth is not capable of spontaneously accelerating to such speeds. Angular momentum must be conserved. To spin faster, the Earth would need to gain angular momentum from an external source, such as a massive impact. The likelihood of such a dramatic change under present conditions is extremely low. In fact, the opposite trend is occurring. Tidal interactions with the Moon are gradually slowing the Earth's rotation. The Moon's gravitational pull creates tidal bulges in the oceans. Because the Earth rotates faster than the Moon orbits, these bulges are slightly ahead of the Moon's position. The gravitational interaction transfers angular momentum from the Earth to the Moon, causing the Moon to slowly drift away, and the Earth's rotation to slow. Billions of years ago, a day on Earth was significantly shorter. Geological evidence suggests that hundreds of millions of years ago, a day may have lasted about 22 hours. Earlier in Earth's history, it was shorter still. The Earth's current rotation rate represents a balance shape by billions of years of evolution. It is fast enough to create a 24-hour day-night cycle, strong enough to influence weather patterns and produce an equatorial bulge, but far too slow to threaten the planet's structural integrity or to overcome gravity. If the Earth spun faster, the most immediate and noticeable changes would involve weight distribution, sea levels, atmospheric circulation, and day length. Only at extremely high rotation rates would the outward forces begin to compete seriously with gravity in a way that might allow material to escape. The key takeaway is that gravity sets a powerful boundary. The outward acceleration from rotation must overcome nearly 10 meters per second, squared of gravitational pull to eject material from the surface. At present, it does not come close. Understanding how increasing rotation would alter the planet makes the present state feel less mysterious. The Earth is not delicately balanced on the edge of instability. It operates comfortably within physical limits, and once we consider what would happen if the Earth spun faster, it becomes equally interesting to explore the opposite scenario. What would happen if it stopped spinning altogether? If imagining the Earth spinning faster raises questions about weight, oceans, and stability, then imagining it stopping altogether takes those questions in a very different direction. At first glance, stopping might sound less dramatic than speeding up. After all, 0 feels calmer than 1,000 miles per hour. But in reality, a sudden stop would be far more catastrophic than a gradual increase in speed. To understand why, we need to distinguish between two scenarios. One is a gradual slowing of the Earth's rotation over millions or billions of years. That is already happening due to tidal interactions with the Moon. The other is an abrupt halt, the Earth instantly ceasing to rotate while everything on its surface continues moving. It is the sudden stop that produces extreme consequences. Right now, every point on the Earth's surface is moving eastward due to rotation. At the equator, that speed is about 1,000 miles per hour. At higher latitudes, the speed decreases with distance from the axis, reaching 0 at the poles. If the Earth were to stop rotating instantly, the solid body of the planet would come to rest relative to distant stars. But inertia would prevent objects on the surface from stopping at the same time. Inertia is the tendency of an object to continue moving in a straight line at constant speed unless acted upon by a force. You, the oceans, the atmosphere, and everything not rigidly anchored to the Earth's deep interior would continue moving eastward at your previous rotational velocity. At the equator, that means objects would attempt to move eastward at roughly 1,000 miles per hour relative to the now stationary ground. The result would be immediate and violent. Buildings would experience enormous lateral forces, trees would snap, unanchored structures would be swept away. The atmosphere, still moving at high speed, would generate winds far exceeding the most powerful hurricanes ever recorded. These winds would scour the surface of the planet. The oceans would also continue moving eastward. Massive walls of water would surge across continents. Coastal regions would be inundated, not because of tides in the usual sense, but because of the inertia of billions of tons of water suddenly encountering stationary land masses. This would not be a minor disturbance. It would be a global catastrophe on a scale difficult to exaggerate. However, if instead of stopping suddenly, the Earth's rotation slowed gradually over geological time, the effects would be far more measured. Sea levels would redistribute slowly. The equatorial bulge would decrease as the outward rotational effect diminished. The planet would gradually become more spherical. In that gradual scenario, life would have time to adapt. The length of day would increase. Instead of 24 hours, a full rotation might take 48 hours, then 72, then perhaps hundreds of hours. Longer days would mean longer periods of sunlight followed by longer periods of darkness. This would dramatically affect climate patterns. Regions would experience more intense heating during prolonged daylight and more significant cooling during extended nights. The atmosphere would respond to these new temperature gradients. Weather systems would reorganize, wind patterns would shift. The Coriolis effect, which depends on rotation, would weaken. Large-scale atmospheric circulation would change accordingly. The Coriolis effect currently influences the direction of trade winds, jet streams, and storm systems. If rotation slowed significantly, these patterns would weaken or reorganize. Storm systems might become more symmetrical around pressure centers rather than exhibiting strong rotational structure. Ocean currents would also change. Present-day currents like the Gulf Stream are influenced by Earth's rotation and the Coriolis effect. With slower rotation, the balance of forces governing ocean circulation would shift, altering global heat distribution. If the Earth stopped rotating entirely relative to the Sun, meaning one side always faced the Sun while the other remained in perpetual darkness, the consequences would be even more extreme. In that case, one hemisphere would experience continuous daylight, while the opposite hemisphere would remain in constant night. The sunlit side would heat relentlessly. The dark side would cool dramatically. Temperature differences between the two hemispheres would drive enormous atmospheric circulation. Air heated on the sunlit side would rise and flow toward the dark side at high altitude, cool and descend, creating powerful, persistent wind systems. Climate patterns would stabilize into a new equilibrium, but that equilibrium would likely involve harsh contrasts between the illuminated and dark hemispheres. Habitability would concentrate in a band near the terminator, the region between day and night, where temperatures might remain moderate. However, it is important to clarify that even if the Earth stopped rotating relative to distant stars, it would still orbit the Sun. That means the day-night cycle would continue over the course of a year. The scenario of one side permanently facing the Sun would only occur if Earth became tidally locked to the Sun, as the Moon is tidally locked to Earth. Tidal locking with the Sun is extremely unlikely for Earth under current conditions. The gravitational interaction is not strong enough at this distance to produce such locking within the Sun's lifetime. Returning to the idea of rotation ceasing, we must also consider angular momentum. Angular momentum is conserved unless acted upon by an external torque. The Earth possesses enormous angular momentum due to its rotation. To stop that rotation instantly would require an equally enormous external force or torque. Such a force does not exist under natural circumstances. Even massive impacts would be unlikely to cancel Earth's angular momentum entirely. They might alter the rotation rate or tilt the axis, but complete cancellation would be extraordinarily difficult. In reality, the Earth's rotation is gradually slowing. The day lengthens by about 1.7 milliseconds per century. This change is primarily due to tidal friction caused by the Moon. As ocean tides rise and fall, friction between water and the ocean floor dissipates energy, gradually transferring angular momentum to the Moon's orbit. Over billions of years, this process could continue to lengthen the day significantly. Eventually, Earth and the Moon may become tidally locked to one another, with the same side of Earth always facing the Moon. But that timescale extends far beyond the current age of human civilization. The essential point is that rotation is not just a background feature of Earth's motion. It shapes the length of day, influences weather and ocean currents, contributes to the planet's shape, and interacts with gravitational forces in measurable ways. If the Earth stopped spinning suddenly, the consequences would be immediate and devastating due to inertia. If it slowed gradually, the planet would adapt physically, though climate and ecosystems would undergo major transformations. The stability we experience now is the result of a long-standing balance between rotation, gravity, and angular momentum. The Earth spins fast enough to produce a 24-hour cycle and an equatorial bulge, but not so fast as to threaten structural integrity. It slows slowly enough that life can evolve within the changing conditions. Understanding what would happen if the Earth stopped spinning highlights something important. The absence of dramatic effects today is not because rotation is insignificant. It is because the rotation is steady, deeply integrated into the planet's structure, and governed by physical laws that enforce stability over vast timescales. And once we see how inertia would amplify the consequences of a sudden stop, it becomes clear why shared motion, the fact that the atmosphere, oceans, and land all rotate together, is essential to maintaining the calm stability we take for granted. If the Earth is spinning at roughly 1,000 miles per hour at the equator, and if inertia causes objects to continue moving when a surface stops abruptly, then another question naturally follows. Why doesn't the atmosphere lag behind? Why isn't there a permanent planet-wide wind blasting from west to east at extreme speed as the solid Earth rotates beneath a relatively stationary layer of air? At first glance, it might seem plausible that the air should behave differently from rock and soil. After all, air is not rigid. It flows. It moves easily. It does not appear firmly attached to the ground. So why doesn't the Earth simply spin inside its own atmosphere? The answer is that the atmosphere is not independent of the planet. It is gravitationally bound to it. The same gravitational force that holds you to the surface also holds trillions upon trillions of air molecules within Earth's gravitational field. The atmosphere formed alongside the planet and shares its rotational motion. To understand this properly, it helps to return to the concept of inertia and shared motion. Every object on Earth, including the air, is already moving eastward at the rotational speed appropriate for its latitude. At the equator, that is about 1,000 miles per hour relative to distant stars. At higher latitudes, the speed is lower. The atmosphere did not start out stationary while the Earth began spinning underneath it. From the earlier stages of Earth's formation, gases were part of the rotating system. As material coalesced under gravity to form the planet, angular momentum was conserved. The gas that became the atmosphere inherited the same rotational motion as the solid body of the Earth. Gravity plays a central role here. Air molecules are constantly moving in random directions at high speeds due to thermal energy. At room temperature, the average speed of nitrogen and oxygen molecules is on the order of hundreds of meters per second. That is several hundred miles per hour in random directions. However, this random motion is superimposed on a large-scale eastward motion shared with the rotating Earth. The key point is that the atmosphere as a whole rotates along with the planet because gravity keeps it bound. If gravity were absent, the atmosphere would disperse into space. But because Earth's gravitational pull is strong, most atmospheric molecules do not reach escape velocity. Escape velocity at the surface is about 25,000 miles per hour. That is far greater than the typical speeds of air molecules, even at high temperatures. So while individual molecules move randomly in all directions, the overall bulk of the atmosphere remains attached to the rotating Earth. Another way to think about this is to imagine a sealed rotating container. Suppose you have a large spherical chamber filled with gas. If you begin rotating the chamber gradually and then maintain a constant rotation rate, the gas inside will eventually rotate along with the container. Friction between the gas and the container walls transfers angular momentum to the gas until equilibrium is reached. In the case of Earth, the container is not sealed, but gravity plays an equivalent role. The lower layers of the atmosphere are in direct contact with the surface. Friction between air and ground transfers momentum. Over time, this interaction ensures that the atmosphere rotates with the planet. If the Earth suddenly stopped spinning, as discussed earlier, the atmosphere would indeed continue moving eastward due to inertia. That would generate extreme winds. But in the present steady state, there is no abrupt change to trigger such a mismatch. The atmosphere and surface move together. This does not mean that the atmosphere is perfectly locked to the surface at all times. Wind patterns exist precisely because air moves relative to the ground. Pressure differences caused by uneven heating drive air from high-pressure regions to low-pressure regions. These movements are modified by Earth's rotation through the Coriolis effect. The Coriolis effect arises because different latitudes move at different linear speeds due to rotation. Air moving north or south retains its original eastward momentum. As it shifts latitude, it encounters ground moving at a different speed, causing an apparent deflection. For example, air moving from the equator toward the poles carries higher eastward velocity than the ground at higher latitudes. As a result, it appears to veer eastward relative to the surface. Similarly, air moving from higher latitudes toward the equator appears to veer westward. These deflections create large-scale wind systems such as trade winds and jet streams. But even these winds represent relatively small differences compared to the overall rotational motion shared by atmosphere and planet. It is also useful to consider the vertical structure of the atmosphere. The lowest layer, the troposphere, is where most weather occurs. Above it lie the stratosphere, mesosphere, and thermosphere. The density of air decreases rapidly with altitude. Near the surface, friction between air and ground ensures strong coupling. Higher up, the air is thinner and less directly influenced by surface friction. Yet even at high altitudes, the atmosphere largely rotates with the Earth. Measurements from satellites and high-altitude balloons confirm that the upper atmosphere participates in the planet's rotation. The entire atmosphere exists within Earth's gravitational field. Gravity does not distinguish between solid rock and gas. It pulls equally on all mass. The difference lies in how materials respond to forces, not in whether they are bound. Consider what would happen if the Earth rotated much faster. As discussed previously, outward centrifugal effects would increase. At sufficiently high rotation rates, the effective gravitational pull at the equator would decrease significantly. In that scenario, the atmosphere near the equator could expand outward. If rotation approached the critical speed where outward acceleration equaled gravity, the atmosphere at the equator would struggle to remain attached. Gas could begin to escape more easily from equatorial regions. But at the current rotation rate, gravity remains dominant. The outward acceleration from rotation is tiny compared to gravitational acceleration. The net inward force keeps air molecules bound. Another important factor is that the atmosphere is not a rigid shell. It responds dynamically to heating, cooling, and pressure differences. The sun heats the equatorial regions more strongly than the poles. Warm air rises, cooler air sinks. These convection patterns redistribute energy around the globe. Earth's rotation modifies these patterns, but it does not override gravitational binding. The atmosphere does not trail behind the Earth, because it is not an external object through which the planet moves. It is part of the rotating system. This shared motion is also why aircraft can fly normally without compensating for 1,000-mile-per-hour ground speed. When a plane takes off, it already possesses the eastward rotational velocity of the Earth. It does not need to accelerate from zero relative to distant stars. It only needs to change its speed relative to the surrounding air. If a plane flies eastward, it adds to its existing rotational velocity relative to the Earth's center. If it flies westward, it subtracts from that velocity relative to distant stars. But within the Earth atmosphere system, its motion is measured relative to the air and ground. The absence of a constant high-speed eastward wind is therefore not mysterious. It is a direct consequence of shared angular momentum and gravitational binding. The atmosphere is not being left behind because there is nothing external for it to lag against. The Earth and its atmosphere rotate together as a single gravitationally bound system. Recognizing this reinforces a broader theme that has appeared throughout this discussion. Stability arises from shared motion and balance forces. Gravity holds the system together. Rotation shapes its behavior. But because everything participates in that rotation, the dramatic effects one might imagine simply do not occur under steady conditions. And once we understand why the atmosphere remains with the Earth, it becomes easier to examine how rotation does influence the movement of air and water in more subtle but profound ways. The Earth's rotation does not merely give us day and night. It does not simply explain why you are not thrown into space. It also quietly organizes the movement of air and water across the entire planet. Weather patterns, trade winds, jet streams, ocean currents, all of them are shaped, redirected, and structured by the fact that the ground beneath them is turning. To understand this properly, we need to step back from the idea of rotation as a dramatic force and instead see it as a subtle but persistent influence on moving fluids. The atmosphere and oceans are not rigid. They flow. They respond to temperature differences, pressure gradients, and gravitational pull. But because they exist on a rotating sphere, their motion does not follow simple straight lines. Let's begin with heating. The sun does not warm the Earth evenly. The equator receives more direct sunlight than the poles. This means equatorial regions absorb more solar energy and become warmer on average. Warm air rises. As it rises, it expands and cools. Cooler, denser air sinks elsewhere to replace it. This sets up large-scale convection patterns. If the Earth did not rotate, this heating contrast would likely create a relatively simple circulation pattern. Warm air would rise near the equator, flow toward the poles at high altitude, cool and sink there, then flow back along the surface toward the equator. The system would organize into two large circulation cells, one in each hemisphere, but the Earth does rotate, and rotation complicates that simple picture. When air moves across the surface, northward or southward, it carries with it the eastward momentum it had at its original latitude. Remember that the surface speed due to rotation is greatest at the equator and decreases toward the poles. That difference in eastward speed becomes crucial. Imagine a parcel of air starting at the equator and moving northward. At the equator, the surface is moving eastward at about 1,000 miles per hour relative to distant stars. At higher latitudes, the ground moves eastward more slowly because the circular path is smaller. As that parcel of air moves north, it retains its higher eastward velocity. Compared to the ground beneath it at higher latitudes, it is now moving faster eastward. From the perspective of someone on the surface, the air appears to deflect to the right in the northern hemisphere. This apparent deflection is known as the Coriolis effect. It is not a force in the traditional sense, but a consequence of observing motion in a rotating frame of reference. In the southern hemisphere, the deflection is to the left. The Coriolis effect does not create motion on its own. It modifies motion that is already happening due to pressure differences, but its influence becomes increasingly important at larger scales. Because of this effect, the simple two-cell convection pattern breaks into three main circulation cells in each hemisphere: the Hadley cell near the equator, the Ferrel cell in mid-latitudes, and the polar cell near the poles. In the Hadley cell, warm air rises near the equator and moves poleward at high altitude. As it moves, it is deflected eastward. Eventually it cools and sinks around 30 degrees latitude. At the surface, air flows back toward the equator. That returning flow, deflected westward by the Coriolis effect, forms the trade winds. The trade winds are steady, predictable winds blowing from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. They played a major role in historical navigation. Their existence is a direct result of the interaction between solar heating and Earth's rotation. In mid-latitudes, the Ferrel cell creates prevailing westerlies, winds that generally blow from west to east. These winds dominate weather patterns in regions like North America and Europe. Storm systems in these regions tend to move west to east because they are embedded in this broader circulation. Near the poles, the polar cells complete the pattern, with cold air sinking and moving equatorward at the surface, again influenced by the Coriolis effect. The rotation of the Earth also gives rise to jet streams, narrow bands of fast-moving air at high altitude. Jet streams form along boundaries between air masses of different temperatures. Because of rotation, these airflows are confined and accelerated into relatively narrow currents that can reach speeds of over 100 miles per hour. Without Earth's rotation, the atmosphere would still circulate due to heating differences, but the organized bands of winds and the characteristic spiraling patterns of storms would not exist in their current form. Now consider storms. Large storm systems, including hurricanes and cyclones, owe their rotation to the Coriolis effect. When warm air rises in a low-pressure system, surrounding air flows inward to replace it. Because of Earth's rotation, that inward-moving air is deflected, creating a spiral pattern. In the northern hemisphere, hurricanes rotate counterclockwise. In the southern hemisphere, they rotate clockwise. This direction difference is entirely due to the Coriolis effect. At the equator itself, hurricanes rarely form. This is because the Coriolis effect is weakest at the equator. Without sufficient deflection, the organized rotation required for a cyclone cannot develop easily. The oceans respond to rotation in similar ways. Surface ocean currents are driven primarily by wind. Trade winds push water westward near the equator. Westerlies push water eastward at mid-latitudes. But because the Earth rotates, these currents do not flow in straight lines across ocean basins. Instead, they are deflected, creating large circular systems known as gyres. In the northern hemisphere, major ocean gyres rotate clockwise. In the southern hemisphere, they rotate counterclockwise. For example, the North Atlantic gyre includes the Gulf Stream, which carries warm water from the Gulf of Mexico northward, along the eastern coast of the United States, and then across the Atlantic toward Europe. The rotation of the Earth influences the path and structure of this current. The Coriolis effect also influences the depth structure of ocean currents through a phenomenon known as Ekman transport. When wind blows across the ocean surface, it drags the uppermost layer of water. Because of rotation, each successive layer of water beneath is deflected slightly relative to the one above it. The net result is that the overall movement of water is at an angle to the wind direction. This angled movement contributes to coastal upwelling and downwelling. In some regions, surface water is pushed away from the coast, allowing deeper, nutrient-rich water to rise. This process supports highly productive marine ecosystems. If the Earth did not rotate, these gyres and deflections would not exist in the same way. Ocean currents would likely flow more directly from equator to poles and back again in response to temperature differences. The distribution of heat across the planet would change dramatically. Rotation also stabilizes climate patterns by distributing energy unevenly but predictably. The interplay between solar heating, gravity, and rotational deflection creates the structured atmospheric circulation that moderates temperature extremes. It is important to remember that the rotation does not act alone. Gravity keeps the atmosphere and oceans bound to the Earth. Solar energy drives temperature differences. Pressure gradients create motion. Rotation shapes that motion. The result is not chaos, but structured complexity. Winds follow preferred paths. Storms rotate in consistent directions. Ocean currents form repeating loops. All of this stems from the same fundamental fact. The Earth is a rotating sphere. When we say the Earth spins at 1,000 miles per hour, it is easy to imagine that number as something disconnected from daily life. But it is directly responsible for the patterns that determine where deserts form, where rainforests thrive, and how heat is transported from equator to poles. The calm you experience at ground level, the absence of dramatic outward force, does not mean rotation is irrelevant. It means that rotation expresses itself not as a violent push, but as a shaping influence on the movement of fluids across the planet. And once you begin to see rotation as something that organizes the atmosphere and oceans rather than threatening to throw them into space, the idea of living on a spinning world feels less precarious and more precisely tuned. When we talk about the Earth spinning at 1,000 miles per hour, it's easy to focus on forces, inertia, and gravity. But the most immediate and familiar consequence of that rotation is far less dramatic and far more personal. It is the cycle of day and night. The Earth rotates once approximately every 24 hours. As it turns, different regions of the planet face the sun and then turn away from it. That simple geometric fact, one hemisphere illuminated while the other is in shadow, creates the daily rhythm that shapes nearly every biological and environmental process on Earth. If the Earth did not rotate, the distribution of sunlight would be radically different. But because it does rotate, every location on the surface experiences alternating periods of light and darkness. This cycle regulates temperature, weather, plant growth, animal behavior, and human activity. During daylight hours, sunlight delivers energy to the surface. Land and water absorb this energy and warm up. Air in contact with the surface heats, expands, and rises. During nighttime, without incoming solar radiation, the surface loses heat through infrared radiation into space. Temperatures drop, air cools and becomes denser. This daily heating and cooling cycle drives local weather patterns such as sea breezes and land breezes. In coastal regions, land heats more quickly than water during the day. Warm air rises over the land, and cooler air from over the water moves in to replace it. At night, the pattern reverses. These patterns exist because the Earth rotates and creates predictable intervals of sunlight and darkness. The 24-hour rotation also defines what we call a solar day. Technically, the Earth rotates slightly more than 360 degrees relative to distant stars during one solar day, because it is also orbiting the Sun. But from the perspective of someone on the surface, the key point is that the Sun appears to rise, move across the sky, and set once every day. This regularity provides a stable temporal framework for life. Biology has evolved around this cycle. Many organisms possess internal clocks, circadian rhythms, that operate on approximately 24-hour cycles. These rhythms regulate sleep, hormone release, metabolism, body temperature, and cognitive performance in humans. In plants, circadian rhythms influence photosynthesis, growth, and flowering. The word circadian comes from Latin roots meaning about a day. These rhythms are not imposed entirely from outside. Even in constant darkness, many organisms maintain roughly 24-hour cycles for a time. But exposure to sunlight synchronizes and stabilizes these rhythms. The rotation of the Earth ensures that sunlight arrives and departs with predictable timing. That predictability allows life to anticipate change rather than merely react to it. Human society has built itself around this rotation as well. Work schedules, agriculture, transportation systems, and communication networks all depend on the daily cycle. Time zones exist because the Earth rotates. When it is noon in one region, it is early morning or late evening elsewhere. That variation arises solely from the planet's spin. Without rotation, there would be no sunrise or sunset in the familiar sense. Instead, if the Earth were tidally locked to the Sun, one hemisphere would experience continuous daylight, while the other remained in perpetual darkness. The region between them would exist in permanent twilight. In such a world, temperature differences would be extreme. The day side would receive constant heating. The night side would radiate heat into space continuously. Atmospheric circulation would likely transport some heat from the day side to the night side, but the balance would be very different from the current system. Under present conditions, rotation moderates temperature extremes by distributing solar heating across the globe over time. Even deserts cool at night. Even polar regions experience extended daylight during summer and extended darkness during winter due to the tilt of the Earth's axis combined with rotation. The tilt of approximately 23.5 degrees adds another layer to the rhythm. As the Earth orbits the Sun, different hemispheres tilt toward or away from sunlight. This creates seasons. But it is rotation that produces the daily pattern within those seasons. A summer day may be long and bright. A winter day may be short and dim, but both are defined by rotation. The 24-hour cycle also influences human psychology and performance. Studies show that cognitive alertness tends to peak during certain times of day and dip during others. Body temperature follows a daily rhythm. Hormones such as melatonin rise and fall in response to light exposure. Disruptions to this cycle, such as shift work, jet lag, or extended exposure to artificial light at night, can interfere with sleep patterns and metabolic regulation. These effects demonstrate how deeply human physiology is connected to Earth's rotation. The concept of midnight and noon only makes sense on a rotating planet. Noon marks the time when the Sun reaches its highest point in the sky at a given location. Midnight marks the midpoint of darkness. Both are defined by orientation relative to the Sun, which changes continuously because of rotation. Even cultural practices reflect this rotation. Calendars track days. Clocks divide them into hours and minutes. The very idea of a day is inseparable from the Earth's spin. From a physical standpoint, the day-night cycle also influences atmospheric stability. Rapid heating during the day can destabilize air masses, leading to convection and thunderstorms. Nighttime cooling can stabilize the atmosphere near the surface, reducing turbulence. On a rotating Earth, the interaction between daily heating cycles and larger-scale circulation patterns creates complex but structured weather behavior. If the Earth rotated more slowly, days would be longer. That would allow more heating during daylight and more cooling at night. Temperature swings would likely increase. Some organisms might struggle to adapt to prolonged exposure to heat or cold. If the Earth rotated more quickly, days would be shorter. Temperature differences between day and night might decrease slightly because there would be less time for heating or cooling during each cycle. Biological rhythms would need to adjust to a different tempo. The current 24-hour period represents a long-evolved state. It is not mandated by physics, but it has become deeply embedded in the biosphere. When we say the Earth spins at 1,000 miles per hour, we often focus on that number in isolation. But what truly matters for life is not the speed itself. It is the duration of one full rotation, the length of the day. The rotation sets the tempo. It defines the alternation of light and darkness. It regulates climate patterns on short timescales. It structures the behavior of living organisms. And because the rotation is steady and predictable, it provides a stable backdrop for life to organize itself. The 1,000-mile-per-hour motion does not feel dramatic at ground level because it is not experienced as force. It is experienced as time passing, as morning turning into afternoon, as afternoon turning into evening. This daily transformation is so familiar that it rarely feels extraordinary, but it is the direct result of a rotating planet moving through space. And once we see how rotation structures both the physical environment and biological rhythms, it becomes clear that Earth's spin is not merely a background statistic. It is the mechanism that gives our world its most fundamental cycle. When people first hear about the Coriolis effect, it is often introduced through a simplified example. Water drains clockwise in one hemisphere and counterclockwise in the other. That explanation is usually exaggerated and, at small scales like sinks and bathtubs, largely irrelevant. The Coriolis effect does not meaningfully control the direction of water spiraling down a household drain. But at planetary scales, across thousands of kilometers, it becomes one of the defining influences on motion. To understand it clearly, we need to return to the idea that Earth is a rotating frame of reference. Motion observed from within a rotating system behaves differently than motion observed from outside it. Imagine you are standing at the equator. You're moving eastward at roughly 1,000 miles per hour relative to distant stars. Now imagine someone at a latitude closer to the pole. That person is also moving eastward due to rotation, but at a slower linear speed because the circular path they trace each day is smaller. The Earth's angular speed, one full rotation per 24 hours, is the same everywhere. But linear speed depends on distance from the axis. The farther you are from the axis, the greater the linear speed. At the equator, the radius of rotation is greatest, so the linear speed is greatest. At the poles, the radius is 0, so the linear speed is 0. This variation in eastward speed with latitude is the foundation of the Coriolis effect. Now imagine a parcel of air located at the equator. It is moving eastward at about 1,000 miles per hour along with the surface. Suppose this air begins to move northward due to a pressure difference. As it moves north, it carries its original eastward momentum with it. But the ground beneath it at higher latitudes is moving eastward more slowly. That means, relative to the ground, the air is moving faster eastward than the surface below. To someone standing on the surface, the air appears to curve or deflect to the right of its intended path. In the southern hemisphere, the geometry reverses. Air moving toward the equator from higher southern latitudes carries less eastward momentum than the surface it encounters. From the perspective of someone standing on the rotating Earth, the motion appears deflected to the left. This apparent deflection is what we call the Coriolis effect. It is not a force in the sense of gravity or electromagnetism. It arises because we are observing motion within a rotating reference frame. If we step outside the Earth's rotation and imagine watching from space. The air is simply moving in straight lines relative to distant stars, modified by pressure gradients and gravity. The curved paths only appear when described relative to the rotating surface. The strength of the Coriolis effect depends on two main factors: the speed of the moving object and the latitude. It is zero at the equator and strongest at the poles. This is because the component of rotational motion that produces the deflection increases with latitude. At the equator, air moving directly north or south does not experience significant deflection from Coriolis forces. That is one reason why large cyclonic storms rarely form exactly at the equator. There is insufficient rotational deflection to organize the inward-flowing air into a spiral. As you move toward mid-latitudes, the Coriolis effect strengthens. In the northern hemisphere, moving objects are deflected to the right of their direction of travel. In the southern hemisphere, they are deflected to the left. This deflection shapes large-scale wind patterns. Trade winds, which blow from east to west in tropical regions, exist partly because of the Coriolis effect acting on air moving toward the equator from higher latitudes. Similarly, the prevailing westerlies at mid-latitudes arise because of air moving poleward and being deflected eastward. Storm systems provide a clear visual demonstration. In the northern hemisphere, low-pressure systems rotate counterclockwise. Air flows inward toward the low-pressure center, but as it does, it is deflected to the right. The result is a spiraling motion. In the southern hemisphere, the same process produces clockwise rotation around low-pressure systems. The difference is purely geometric, arising from the opposite direction of deflection. The Coriolis effect also influences ocean currents. Winds transfer momentum to the ocean surface. Because the Earth rotates, the water does not simply move in the direction of the wind. Instead, each layer of water beneath the surface is deflected slightly relative to the layer above. This creates a spiral structure known as the Ekman spiral. The net movement of water in this system is at an angle to the wind direction. In the northern hemisphere, it is roughly 90 degrees to the right of the wind. In the southern hemisphere, it is 90 degrees to the left. This deflection helps form large rotating systems of ocean currents called gyres. These gyres circulate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. The Gulf Stream, for example, is part of a large clockwise gyre in the North Atlantic. It transports warm water from lower latitudes toward Europe, influencing regional climate. Without the Coriolis effect, ocean currents would likely follow simpler north-south paths driven by temperature differences alone. The Coriolis effect also plays a role in long-range ballistics and aviation. When projectiles travel over long distances, especially toward higher latitudes, their paths deviate slightly due to Earth's rotation. These deviations must be accounted for in precision targeting. However, it is important to keep the scale in perspective. The Coriolis effect is negligible at small scales. In a bathtub or sink, water rotation is determined primarily by the shape of the basin and initial motion of the water. The Coriolis effect becomes significant only when dealing with motions over hundreds or thousands of kilometers and over long durations. At its core, the Coriolis effect is a demonstration of how rotation modifies motion within a system. It does not create motion from nothing. It bends motion that already exists due to other forces. The reason this matters in the context of Earth's rotation is that it shows how a 1,000-mile-per-hour spin does not manifest as a single dramatic force, pushing everything outward. Instead, it subtly reshapes the way fluids move across the planet. Weather systems spiral, jet streams curve, ocean currents loop, all because we live on a rotating sphere. Understanding the Coriolis effect reinforces a broader point. The Earth's rotation is not something that throws you into space. It is something that shapes the patterns of motion around you. It organizes the atmosphere into circulation cells. It guides storms into spirals. It steers currents into gyres. The spin is steady. The forces are balanced. The effects are persistent but structured. And once we recognize that motion on a spinning world behaves differently than motion on a stationary one, the larger picture comes into focus. We are not simply standing on a moving rock. We are part of a rotating, gravitationally bound system whose motion defines the behavior of air, water, and climate itself. Up to this point, we have focused on the Earth's rotation, the fact that the planet spins once every 24 hours, carrying you eastward at up to 1,000 miles per hour at the equator. But that rotation is only one layer of motion. It is not even the fastest motion you are currently participating in. While the Earth spins on its axis, it is also orbiting the Sun. The Earth travels around the Sun at an average speed of about 67,000 miles per hour, or roughly 30 kilometers per second. That number is far larger than 1,000 miles per hour. It is more than 60 times faster, and yet, just like the rotation of the Earth, you do not feel that motion either. To understand why, we need to examine what orbit actually means. The Earth does not orbit the Sun in the sense of being pulled around like an object on a string. Instead, it is in continuous free fall toward the Sun. Gravity from the Sun pulls the Earth inward. At the same time, the Earth has sideways motion, tangential velocity, that carries it forward. The combination of inward gravitational pull and forward inertia produces a curved path. The Earth keeps missing the Sun because it is always moving sideways fast enough that, as it falls inward, the surface of the Sun curves away beneath it. This is what orbit is: perpetual free fall with sufficient sideways velocity. At 67,000 miles per hour, the Earth completes one orbit in about 365.25 days. That speed sounds enormous compared to everyday experience. But as with rotation, the key factor is not speed alone, it is acceleration. When you ride in a car, you feel acceleration when the car speeds up, slows down, or turns. In orbit, the Earth's velocity is constantly changing direction as it moves along its curved path around the Sun. That change in direction represents acceleration, specifically centripetal acceleration directed toward the Sun. However, this acceleration is relatively small compared to gravity at the Earth's surface. The Sun's gravitational pull at Earth's distance produces an acceleration of about 0.006 meters per second squared. That is tiny compared to Earth's surface gravity of 9.8 meters per second squared. More importantly, everything on Earth shares this orbital motion. The ground beneath you, the oceans, the atmosphere, and your own body are all falling toward the Sun together. There is no relative motion between you and the Earth caused by orbit. This situation is similar to astronauts in orbit around Earth. They are moving at about 17,500 miles per hour. Yet they feel weightless because they and their spacecraft are falling toward Earth together. There is no surface pushing up on them to create the sensation of weight. In our case, the Sun's gravity pulls equally on you and on the Earth beneath you. The force is nearly uniform across the planet. Because you are gravitationally bound to the Earth much more strongly than to the Sun, you remain attached to the Earth while both of you orbit the Sun together. There is no internal stress from this motion, because the acceleration toward the Sun is essentially the same for everything in the Earth system. This uniform acceleration is what prevents you from feeling the orbital motion. If, hypothetically, the Sun's gravitational pull suddenly increased dramatically, you would feel the difference because the acceleration would change. But under stable conditions, the Earth's orbit is steady and predictable. The scale of this motion can be difficult to visualize. In 1 second, the Earth moves about 30 kilometers along its orbit. In 1 minute, that becomes 1,800 kilometers. In 1 hour, about 108,000 kilometers. Over the course of a year, the Earth travels roughly 940 million kilometers around the Sun. And yet, from your perspective, the Sun appears to rise and set once per day due to Earth's rotation. The annual orbit reveals itself more subtly through the changing positions of stars at night and the progression of seasons. The orbital motion combines with axial tilt to produce seasons. Because the Earth's axis is tilted about 23.5 degrees relative to its orbital plane, different hemispheres receive more direct sunlight at different times of year. As the Earth orbits the Sun, the tilt remains oriented in the same direction relative to distant stars. This means that during part of the year, the northern hemisphere tilts toward the sun, receiving more direct sunlight and experiencing summer. 6 months later, it tilts away, producing winter. The southern hemisphere experiences opposite seasons. Without orbital motion, there would be no seasonal cycle. The sun's position relative to Earth would not change in the same way. The variation in daylight length over the year would not occur. From a purely mechanical standpoint, Earth's orbital speed is balanced precisely by the sun's gravitational pull. If the Earth moved more slowly, gravity would pull it inward toward the sun. If it moved faster, it would drift outward into a more distant orbit. The current balance keeps Earth at an average distance of about 150 million kilometers from the sun, a distance that allows liquid water to exist on the surface. The orbital speed is not arbitrary. It is determined by gravitational physics and the conservation of angular momentum. Just as with rotation, the orbital motion does not feel dramatic because it is smooth and shared. There are no abrupt accelerations. There is no external stationary frame within your immediate environment to highlight the movement. To illustrate how relative motion works at this scale, imagine again sitting in a smoothly moving train. If the train moves at constant speed along straight tracks, you feel stationary inside. Now imagine that train is moving along a very gentle, massive curve, so gentle that you cannot perceive the curvature directly. That is analogous to Earth's orbit. The curvature of the path is enormous, with a radius of about 150 million kilometers. The inward acceleration required to maintain that orbit is small compared to the forces you experience due to Earth's gravity. The result is that orbital motion remains unnoticed in daily life. It is also important to recognize that the Sun itself is moving. The entire solar system orbits the center of the Milky Way galaxy at roughly 490,000 miles per hour. Meanwhile, the Milky Way moves relative to other galaxies. When you combine all these motions, Earth's rotation, Earth's orbit around the Sun, the Sun's orbit around the galaxy, your actual velocity through space relative to distant cosmic structures is enormous, yet you feel none of it directly. The reason is consistent across all scales. Motion is only meaningful relative to something else, and acceleration is what produces sensation. In the absence of changing acceleration within your local frame, motion remains invisible. Understanding Earth's orbital speed adds perspective to the earlier discussion of 1,000 miles per hour. That rotational speed, which initially sounded alarming, is modest compared to 67,000 miles per hour around the Sun. And just as gravity binds you to the spinning Earth, it also binds the Earth to its orbital path. The planet is not careening randomly through space. It follows a stable trajectory determined by gravitational interaction with the Sun. The calm you experience at ground level is not evidence that you are stationary in the universe. It is evidence that you are part of a stable, gravitationally bound system moving coherently through space. And once you consider that the Earth is spinning while orbiting, and orbiting while the solar system itself moves, the idea of standing still becomes even more relative than it first appeared. By now, the numbers have grown steadily larger, 1,000 miles per hour due to Earth's rotation, 67,000 miles per hour as the Earth orbits the Sun, nearly 500,000 miles per hour as the solar system moves around the center of the Milky Way. At each layer, the motion increases, and yet, despite these immense speeds, nothing appears to be flying apart. So why doesn't the solar system tear itself to pieces? The answer is not that space is empty and therefore harmless. The answer lies in the balance between motion and gravity. Just as gravity prevents you from being flung off the spinning Earth, gravity also binds planets to the Sun and holds the solar system together as a coherent structure. Let's start with the Sun. The Sun contains about 99.8% of the total mass of the solar system. That mass generates an enormous gravitational field. Every planet, asteroid, comet, and dust particle in the solar system is influenced by that gravitational pull. The planets are not simply drifting through space near the Sun. They are in orbit because their sideways velocity is precisely balanced by the inward gravitational pull of the Sun. If a planet moved more slowly, gravity would draw it inward into a smaller orbit. If it moved more quickly, it would move into a larger orbit or potentially escape entirely. This balance is governed by well-understood physics. For a planet in a stable orbit, gravitational force provides the centripetal acceleration required to keep the planet moving along its curved path. Without gravity, planets would move off in straight lines due to inertia. Without inertia, meaning without sideways velocity, they would fall directly into the Sun. The solar system does not tear itself apart because gravity is strong enough to bind its components together. Consider Earth's orbit again. At 67,000 miles per hour, Earth might seem to be moving fast enough to escape the Sun's pull. But escape velocity at Earth's distance from the Sun is about 94,000 miles per hour. Earth's orbital speed is lower than that. It is precisely tuned by gravitational dynamics. The same principle applies to other planets. Mercury, which orbits closer to the Sun, moves much faster, about 107,000 miles per hour, because it must counteract stronger gravitational pull at its smaller orbital radius. Neptune, far from the Sun, moves more slowly, about 12,000 miles per hour, because the Sun's gravitational pull is weaker at that distance. The distribution of speeds is not random. It follows directly from the inverse square law of gravity. The gravitational force decreases with the square of distance. Orbital speed adjusts accordingly to maintain equilibrium. It is also important to recognize that planets do exert gravitational forces on one another. Jupiter, for example, is massive enough to influence the orbits of other planets and to capture or deflect comets. These gravitational interactions cause subtle perturbations in planetary orbits. However, these perturbations are generally small relative to the dominant gravitational influence of the Sun. The solar system has evolved over billions of years into a relatively stable configuration. Stability does not mean perfect rigidity. Orbits shift slightly over time. Gravitational resonances occur. For example, some asteroids occupy stable orbital ratios with Jupiter. These resonances can either stabilize or destabilize certain regions of space. But overall, the system does not fly apart because gravitational binding outweighs the tendency of objects to move off in straight lines. Another way to understand this is to compare the solar system to a rotating system we have already discussed, the Earth itself. The Earth does not tear itself apart because gravity holds it together against the outward effects of rotation. Similarly, the solar system does not disperse because the Sun's gravity holds its components in orbit against their inertial tendency to move in straight lines. Angular momentum is central to this stability. The solar system formed from a rotating cloud of gas and dust. As the cloud collapsed under gravity, conservation of angular momentum caused it to spin faster. Much of the material concentrated at the centre to form the Sun. The remaining material flattened into a rotating disk from which planets formed. The planets inherited angular momentum from this disk. Their orbital motion today reflects the conditions of that early formation period. Over billions of years, gravitational interactions have smoothed and refined the system. The solar system is not static, it evolves. Comets are occasionally ejected. Asteroids collide. Planets experience gradual shifts in orbital parameters. But these changes occur within a framework defined by gravitational binding and conservation laws. It is also worth considering that the solar system is not isolated in a perfectly calm environment. The Milky Way galaxy exerts gravitational influence. Passing stars can slightly perturb the outer reaches of the solar system, particularly the distant Oort cloud of icy bodies. Even so, the Sun's gravitational influence dominates within its immediate region of space. The solar system occupies a gravitational well carved out by the Sun's mass. Within that well, planets remain bound unless acted upon by an external force strong enough to overcome the Sun's pull. This gravitational binding extends to smaller objects as well. Moons orbit planets because of planetary gravity. For example, Earth's moon orbits at about 2,300 miles per hour relative to Earth. It does not drift away because its speed is balanced by Earth's gravitational pull. If the moon moved faster than escape velocity relative to Earth, it would leave. If it moved slower, it would spiral inward. The current speed is stable under present conditions. In the broader cosmic context, even galaxies do not simply tear apart under their own rotation, because gravitational attraction binds stars within them. Dark matter, though not directly visible, contributes significantly to the gravitational structure of galaxies. At every scale, from you standing on Earth, to Earth orbiting the Sun, to the solar system orbiting the galaxy, stability arises from the balance between motion and gravity. The high speeds involved are not signs of instability. They are necessary components of orbital motion. Speed without gravity would mean dispersion. Gravity without speed would mean collapse. Together they produce stable, repeating paths. The solar system does not tear itself apart because the forces holding it together are immense and consistent. The Sun's mass dominates. Orbital velocities are matched precisely to gravitational requirements. Conservation laws enforce coherence. Understanding this removes the impression that high velocity equals danger. Motion through space at tens of thousands of miles per hour is not inherently destructive. It is destructive only if unbalanced by gravitational binding or altered abruptly, and as we expand our perspective from planetary rotation to solar orbit to galactic motion, one theme remains constant. What feels like stillness at ground level is simply participation in a larger structured movement governed by fundamental physical laws. By now, it should feel increasingly clear that the sense of standing still is not as straightforward as it first appears. The Earth rotates, it orbits the Sun. The Sun orbits the center of the galaxy. And yet, you experience none of this motion directly. The ground feels solid. The room feels stationary. The air feels calm. To understand why this illusion of stillness is so convincing, we need to look more closely at two ideas, inertia and relativity. And this is where Albert Einstein enters the discussion, not because he changed the fact that Earth spins, but because he reshaped how we understand motion itself. Let's begin with inertia. Inertia is the tendency of an object to resist changes in its state of motion. If something is at rest, it tends to stay at rest unless acted upon by a force. If something is moving at constant velocity in a straight line, it tends to keep moving that way unless acted upon by a force. This principle was formalized by Isaac Newton as his first law of motion, but it becomes especially meaningful when we consider large-scale motion like Earth's rotation and orbit. Right now, you are moving eastward due to Earth's rotation. You're moving around the Sun. You are moving through the galaxy. But you do not feel these motions because they are steady. There is no change in velocity that your body can detect. The human sensory system is not designed to measure constant velocity. It is designed to detect acceleration, changes in speed or direction. When a car accelerates, you feel pushed back. When it brakes, you lurch forward. When it turns sharply, you feel pulled sideways. These sensations arise because your body resists changes in motion due to inertia. Your inner ear senses acceleration, not velocity. If you were placed inside a perfectly smooth spaceship drifting through space at constant speed, you would feel weightless and stationary. Without external reference points, you would have no way to determine whether you were moving at 10 miles per hour or 10,000 miles per hour. This is not a limitation of your senses, it is a fundamental property of physics. Galileo was one of the first to recognize this clearly. He argued that if you were below deck on a smoothly sailing ship, you could not tell whether the ship was moving at constant velocity or at rest simply by observing objects inside the cabin. Water dripping, insects flying, or balls tossed would behave the same way. Einstein extended this idea in his theory of special relativity. One of the central principles of special relativity is that the laws of physics are the same in all inertial frames of reference. frames moving at constant velocity relative to one another. There is no preferred inertial frame, no universal background that defines true rest. This means there is no absolute state of stillness in the universe. If you say, "I am at rest," that statement is incomplete. You're at rest relative to something, your chair, your house, the Earth's surface. But relative to the Sun, you're moving at 67,000 miles per hour. Relative to the centre of the Milky Way, you're moving even faster. None of these frames is more correct than the others in an absolute sense. They are simply different perspectives. Einstein's work showed that not only is motion relative, but measurements of space and time themselves depend on motion. At extremely high speeds, close to the speed of light, time slows down and lengths contract relative to stationary observers. These effects are negligible at Earth's orbital speed, but they are real and measurable in high-speed experiments. What matters for our discussion is this. There is no cosmic anchor point labelled truly still. The illusion of stillness arises because you and your environment share the same motion. You're not moving relative to your immediate surroundings. And because your body detects only changes in motion, constant velocity goes unnoticed. Even circular motion, like Earth's rotation, produces only subtle acceleration. The centripetal acceleration at the equator due to rotation is tiny compared to gravity. It does not overwhelm your sensory system. Inertia also explains why you are not flung off the planet when you jump. When you leap into the air, you retain your horizontal velocity. You and the Earth continue moving together. Gravity pulls you downward, not backward or sideways. Now consider a more abstract example. Imagine you're inside a sealed, windowless box floating in deep space. The box is moving at constant velocity. There is no vibration, no sound, no external reference points. From inside, you cannot determine whether you're drifting through space or at rest relative to some distant object. This thought experiment is not just philosophical. It is a core concept in relativity. Physics inside that box works the same whether the box is stationary or moving uniformly. The Earth functions in a similar way. You live inside a rotating and orbiting system. Because the motion is steady and shared, it feels stationary. Einstein also introduced the idea that gravity is not simply a force in the traditional sense, but a curvature of space-time caused by mass. In general relativity, objects follow curved paths not because they are pulled by an invisible string, but because space-time itself is curved around massive objects like the Sun. From that perspective, Earth's orbit is not a struggle between motion and gravity. It is a natural path through curved space-time. Although this framework is more advanced than necessary to answer why you do not feel motion, it reinforces the idea that what we perceive as forces and motion depend heavily on perspective. Stillness is not a universal condition, it is a local one. When you stand on the ground, you are at rest relative to the Earth's surface. The Earth is rotating, the Earth is orbiting. The solar system is moving through the galaxy. Yet within your local frame, physics behaves predictably and calmly. The illusion of stillness is not deception. It is the natural result of being embedded within a coherent moving system. Inertia ensures that constant motion does not produce sensation. Relativity ensures that no frame of constant motion is privileged over another. The 1,000-mile-per-hour spin, the 67,000-mile-per-hour orbit, the galactic motion. None of these violate the sense of stability because they are steady and shared. And once you recognize that stillness is always relative, the question shifts. Instead of asking why you do not feel motion, it becomes more interesting to ask whether motion itself might be something deeper, whether time, change, and motion are more fundamental than stillness in the first place. At this point, the original question has expanded far beyond the surface of the Earth. We began with a simple number, 1,000 miles per hour, and the intuitive concern that such speed should feel dramatic. But as each layer has unfolded, the scale of motion has grown. Earth spins, Earth orbits, the solar system moves, and now we arrive at the broader perspective. everything is moving. There is no fixed platform beneath the universe. The Earth rotates once every 24 hours. It orbits the Sun at about 67,000 miles per hour. The Sun orbits the center of the Milky Way galaxy at roughly 490,000 miles per hour. And the Milky Way itself is moving relative to other galaxies at hundreds of thousands of miles per hour. Zoom out further, and motion continues. Galaxies are not scattered randomly in space without movement. They participate in the large-scale expansion of the universe. On cosmic scales, space itself is expanding. Distant galaxies are receding from one another, not because they are traveling through space in the conventional sense, but because the fabric of space between them is stretching. This does not mean that everything is flying apart chaotically. Gravitationally bound systems, such as solar systems and galaxies, remain intact because gravity overcomes the effect of cosmic expansion at smaller scales. But beyond those scales, expansion dominates. The result is that motion is not an exception in the universe. It is the default condition. The idea of standing still is a local approximation. It is useful for everyday life, but it does not represent an absolute state. Consider your current situation. You are sitting, standing, or lying down. Relative to the room, you are at rest. Relative to the Earth's surface, you are at rest. But relative to the Sun, you are moving at tens of thousands of miles per hour. Relative to the galaxy, you are moving faster still, and yet nothing feels unstable. The reason, as we have seen repeatedly, is that you are part of a coherent system. You share motion with your environment. Forces are balanced. Acceleration is minimal. Stability arises not from the absence of motion, but from the consistency of motion. Even on smaller scales, motion is constant. The atoms in your body are not stationary. Electrons move within atomic structures. Molecules vibrate due to thermal energy. At room temperature, molecular motion is continuous and rapid. The apparent solidity of objects emerges from electromagnetic interactions and quantum principles, not from true stillness at the microscopic level. On planetary scales, tectonic plates shift slowly. The Moon recedes from Earth by a few centimeters per year. The Earth's rotation slows gradually. None of these motions are perceptible moment to moment, but they are real. At galactic scales, stars orbit the center of the Milky Way in complex paths. Our Sun completes one galactic orbit roughly every 225 to 250 million years. During that time, entire continents on Earth shift, climates change, and species evolve. Even the Milky Way is not static. It is gravitationally interacting with the Andromeda Galaxy. In about 4 billion years, the two galaxies are expected to merge. Their stars will pass one another across vast distances, reshaping the structure of both galaxies. And yet, despite these immense motions and interactions, the universe is not collapsing into chaos at every scale. Structure persists because forces balance motion. Gravity binds systems together. Inertia carries them forward. Angular momentum stabilizes rotation. Conservation laws govern change. The cosmic perspective reveals that motion is layered. You are moving in many ways simultaneously, rotating with Earth, orbiting the Sun, circling the galaxy, traveling through expanding space. But because each motion is smooth and continuous, and because each larger system carries the smaller systems within it, you experience local calm. The sense of stillness is not false, it is contextual. Imagine sitting inside a smoothly moving aircraft at cruising altitude. The plane may be travelling at 500 miles per hour relative to the ground. The Earth beneath it is rotating and orbiting. The galaxy is moving. Yet inside the cabin, a cup of water rests on a tray without disturbance. The stability inside the cabin arises because everything in that cabin shares the same motion. The same principle applies at planetary and cosmic scales. There is also something conceptually important in recognizing that everything is moving. It challenges the intuitive belief that rest is the natural state, and motion is something added. In classical physics, inertia teaches the opposite. Motion at constant velocity is just as natural as rest. Neither requires explanation beyond the absence of force. In the cosmic view, motion is not a disturbance of stillness. It is part of the structure of reality. This perspective does not make daily life unstable. It makes it more precisely understood. You are not precariously balanced on a spinning sphere that could fling you away at any moment. You are part of a gravitationally bound hierarchy of systems, each in motion, each stable within its own scale. The 1,000-mile-per-hour spin that seemed alarming at first becomes modest when compared to orbital and galactic speeds. And even those larger speeds become ordinary within their gravitational context. Everything is moving, but not everything is accelerating violently. The distinction matters. Acceleration is what produces forces you can feel. Constant motion, when shared and balanced, produces stability. When viewed from this broader perspective, the original question, why don't you get thrown into space, no longer feels mysterious. It feels expected. The Earth's rotation is simply one component of a much larger ordered system of motion, and once you recognize that motion defines the universe at every scale, the idea of standing still becomes less about physical immobility and more about relative reference. You're at rest relative to the surface beneath you. That is sufficient for daily life. Beyond that, you are participating in a vast and structured movement that has been unfolding for billions of years. Motion is universal, stability is local, and both coexist without contradiction. We began with a number that sounded unsettling. 1,000 miles per hour, the speed at which the Earth rotates at the equator. On its own, that figure feels incompatible with everyday experience. It suggests force, instability, perhaps even danger. And yet, nothing around you hints at such motion. The floor is steady, the air is calm, a glass of water does not tremble with hidden velocity. As we followed the layers of motion outward, the number grew. 67,000 miles per hour as the Earth orbits the Sun. Nearly 500,000 miles per hour as the solar system circles the center of the Milky Way. Beyond that, the galaxy itself moves within an expanding universe. And still, you feel stationary. The resolution to this apparent contradiction does not lie in denying the motion. The Earth truly spins. It truly orbits. The solar system truly travels through the galaxy. The resolution lies in understanding how motion, gravity, inertia, and relativity work together to produce stability. You're not perched on a spinning disk being flung outward. You are gravitationally bound to a massive planet whose inward pull overwhelmingly exceeds the outward acceleration of rotation. The small centrifugal effect at the equator slightly reduces your weight, but it does not threaten to lift you away. The atmosphere remains with the Earth because it is bound by gravity and shares the planet's rotational motion. The oceans circulate not because the Earth is unstable, but because rotation organizes their movement into structured patterns shaped by the Coriolis effect. Day and night unfold because of rotation, not despite it. Biological rhythms synchronize with a 24-hour cycle created by spin. Weather systems curve and spiral because the ground beneath them is turning. At the next scale, the Earth does not tear away from the Sun because orbital speed and gravitational pull are balanced precisely. Inertia carries the planet forward, while gravity curves its path into a stable orbit. At every level, the same principle appears. Motion alone does not create chaos. Unbalanced acceleration does. In the absence of abrupt changes, shared and steady motion produces calm. Einstein's insight reinforces this. There is no universal state of absolute rest. Motion is always relative. If you and your surroundings share the same velocity, you experience stillness within that frame. The illusion of standing still is not an error. It is the natural consequence of being embedded in a coherent moving system. What feels fixed is fixed relative to you. What feels calm is calm within your frame. Right now, as you sit or stand or lie down, you are rotating with the Earth. You are orbiting the Sun. You're traveling through the galaxy. But you're doing so as part of a stable hierarchy of motion governed by consistent physical laws. The 1,000-mile-per-hour rotation that first sounded dramatic is simply one component of that hierarchy. It shapes the length of the day. It influences winds and currents. It leaves a measurable imprint in the planet's slight equatorial bulge. But it does not threaten to cast you into space. Gravity holds you down. Inertia carries you along. Relativity ensures that constant motion feels like rest within your local frame. Standing still, then, is not the absence of motion. It is participation in motion that is balanced and shared. If you pause for a moment and consider where you are, geographically, astronomically, the perspective shifts slightly. The ground beneath you is not stationary in any absolute sense. It is part of a rotating sphere moving through space. Yet your experience remains stable, because the forces involved are consistent and proportional. The calm you feel is not fragile. It is the result of billions of years of physical equilibrium. And so the question that began this exploration, why don't you get thrown into space, resolves not into mystery, but into structure. The Earth spins at 1,000 miles per hour. It has done so for billions of years. It will continue to rotate, gradually slowing, long after this moment passes. You're not resisting that motion. You are part of it. And in that sense, standing still on a moving world is not a contradiction. It is simply what it means to live inside a stable, rotating universe.